So we're going to talk about prefetching today. This is another fascinating topic. Remember, we're looking into the more processor-centric world in the last third of the lecture. We've talked a lot about memory and data-centric architectures. Now we're going to look more into processor-centric. But keep in mind that some of these techniques that we are going to discuss are so fundamental that they may be employed in data-centric architectures as well. In fact, we've seen examples of prefetching in Tesseract, for example. But now we're going to delve into detail in prefetching. And this has been a technique that has been extremely successful in modern microprocessors and tolerating latency. Of course, as you know, even with this technique, we're still stalling for data. So there's a lot of room for improvement for prefetching mechanisms. And this is also a very interesting and exciting area of research in computer architecture. And this is perhaps an area where a lot of the performance improvements in a modern microprocessor design can come from. How do you handle the data? How do you bring the data into the processor much earlier than the processor actually needs it? Okay, and you're also going to work on this on your lab 4. Okay, basically, I will remind you the memory latency problem because that's the problem that we're trying to solve with prefetching. Let's go over some of these slides relatively quickly. I think you remember this slide very well. By now, we know that memory latency lags behind, and there are good reasons for it. Well, not all the reasons are necessarily good, but there are at least reasons that people use to justify why latency has not been improving. And one of the reasons is, as I mentioned earlier, latency is much more difficult to improve compared to bandwidth and capacity, as we discussed. Okay. And we also know that latency is critical for performance. We saw many applications that are bottlenecked by latency, and we discussed the implications of latency, the implications of reducing latency on these applications, and we saw significant benefits in earlier lectures. If you remember lecture 10, we dedicated that to designing low latency memories and their impact on system performance and system energy. But long memory latency in the end results in a performance bottleneck. And overall, whenever latencies are high, we have problems. So if you want to jog your memory on the importance of latency, lecture 10 provides many different aspects of the importance of latency. For example, if you want to operate on edge devices and relatively quickly get answers, latency becomes even more important. You cannot, you have to process things locally. You cannot go over the network. And while you're processing things locally, if you have real-time requirements, you need to reduce latency as much as possible. So I'm not going to cover all of that. Lecture 10, I think, provides a very good introduction into why applications going forward need even better latency requirements, especially with artificial intelligence applications, for example, or genome analysis applications where we want answers very quickly. Otherwise, it's a life or death situation. Then latency is extremely important. Okay, and we also discussed this work where we said new DRAM types are actually increasing latency, or even if they're not increasing latency, they're not reducing latency. So they're trading off latency sometimes for bandwidth, for example. And this is not necessarily good. And you already are familiar with many of the DRAM types that we've discussed. And unfortunately, some applications lose performance when you go from an older DRAM type to a newer DRAM type in your system. And as a result, and this is one of the reasons is latency is increasing in some of these DRAM designs that are new. And we already discussed this, so you can again refer back to lecture 10 for this. And we said that memory latency remains a critical bottleneck, and there are many other takeaways in this work. Some of them are also related to latency, actually. For example, bank parallelism is not fully utilized. You can tolerate latency by having more parallelism, more concurrency, such that you hide the latency of memory requests. We've discussed that, for example, when we talked about parallelism or batch scheduling, but we've discussed it in other contexts also. But if your bank parallelism is not fully utilized, then you cannot tolerate the increasing latencies. And you cannot tolerate the existing latency also, if that's the case. The third one is also related to latency, actually, because spatial locality is important so that your latency is reduced in the row buffer, for example. If you don't exploit spatial locality, you may actually get row buffer misses, row buffer conflicts. As a result, your latencies increase. Okay. This is unfortunate because if future DRAM types are increasing latency or not reducing latency, that's not good. And we have also discussed techniques for latency reduction, tolerance, and hiding. We call them overall latency tolerance techniques. I'd like to distinguish between these. Clearly, memory latency is important. And if you're in a processor-centric world, you would like to reduce the latency experienced by the processor. But let me distinguish between these three terms just for the sake of it. I think of different things when I say latency reduction, latency tolerance, and latency hiding, let's say. And this is an attempt at distinguishing between them, basically. So reduction, in my opinion, means fundamentally reducing latency as much as possible. And we already covered this. This is more of a data-centric approach. And when you design low latency memories, you're trying to reduce latency as much as possible. This is really fundamentally reducing the latency at its source of the problem. It's not reducing the latency. I don't think reducing latency is the right term to use if you're reducing latency from the processor's perspective. I think reducing latency is the right term to use if you're really reducing latency at the source of it, right? And we've already discussed approaches to do this. You can revisit that. And you've already actually done homework assignments related to that. Hiding latency, on the other hand, which is the third one over here, you may try to hide the latency seen by the processor, right? Basically, you may still have very long latency to get data from memory, but the processor doesn't see it. Why? Because you design caches, for example, and the next time you access the same data in the cache, it hits in the cache. As a result, the processor doesn't see the latency the second time. You've designed prefetchers, like we're going to discuss today, such that prefetchers already bring the data from the memory into the cache or into a prefetch buffer, as we will also discuss, before the processor needs it. As a result, it hides the latency that would otherwise be seen by the processor. Right? The latency still exists. You're not reducing latency fundamentally, but you're trying to hide it from the processor's perspective. So clearly, this is a processor-centric approach. Now, it could also be employed in data-centric systems where processors are much closer to memory. For example, tesseract, as I mentioned. In tesseract, processors are in the logic layer. Still, there are compute units that are separated from the memory. And you may need to hide the latency if that latency is high. Right? Okay, and finally, tolerating or amortizing the latency seen by the processor. This is fundamentally different from hiding the latency. Well, I guess people use hiding latency in this case also, but I like using the term tolerating latency. But basically, in this case, you're not reducing the latency of the request seen by the processor, but you're really amortizing the cost of each request, let's say. Basically, you're overlapping different requests using multi-threading, out-of-order execution, and run-ahead execution. And we've covered some of these, and clearly, digital design and computer architecture. If you have time, we'll actually talk about that. Actually, we will briefly talk about this today in terms of prefetching, and we may actually talk about run-ahead execution. If you remember, in lecture 10, we briefly talked about run-ahead execution, which is a processor-centric approach to tolerate the latency seen by the processor. Basic idea is here, instead of having a single request outstanding, have many requests outstanding, such that you don't pay the cost of the latency for all of those requests separately. You pay the cost once for all of the requests, as much as possible, of course. And clearly, bank level parallelism is important here so that you can service those requests in parallel. And you could generate those requests in different ways, clearly using multi-threading, out-of-order execution, or run-ahead execution. Okay, hopefully this distinction is clear. I think it's good to clarify the different approaches used and different benefits they can lead to. Okay, I guess I will mention one last thing over here in the tolerating latency. Here, you're really trying to reduce the stall time of the processor. Whereas here in caching and prefetching, yes, you are in the end reducing the stall time potentially if you're successful, but you're also reducing the latency seen by the processor of each request. Here, the latency seen by the processor for each request may be the same, right? You still get cache misses. You're not caching and prefetching may not be effective here, but you're tolerating the latency by parallelizing the requests. So that's the fundamental difference over here. Ideally, so if you think about the ideal part, you would reduce latency and you would need none of this at the bottom, clearly. But the bottom two, hiding latency and tolerating latency techniques would not be necessary if you reduce latency to 0. Okay, and I also mentioned this slide, which I used in my PhD proposal, which covers essentially the 4 major conventional latency tolerance techniques: caching, prefetching, multi-threading, and out-of-order execution. And we're not going to go through the details of it, but I'm going to give you pointers to some of these in the next slide. And we may cover some of these later this semester, but unlikely for some of them. So clearly caching is a latency hiding technique from the process perspective. And when it's effective, it's actually good, but when it's not effective, it increases latency seen by the processor because you need to actually access different cache levels, right? So there's a danger in latency hiding techniques. They may actually increase latency when they're not successful. And we've also mentioned that for caching to be really successful, you need to have good locality, right? Hitting once in the cache may not be good enough because the cost of energy in terms of memory access is very large, and bringing the data into the processor actually consumes a lot of energy. And if you're not amortizing the cost of bringing the data into the processor by taking advantage of the cache a lot, then your caching actually may not be good for energy or good for performance in the end. And we've already discussed this, and you've implemented caches. I'm going to give you pointers to more advanced cache management. If you're interested, you can take a look. And we've already covered this in digital design and computer architecture a lot also. But you can also see that these ideas are relatively old ideas, but they're still being improved in the research as well as design communities. Prefetching, we're going to cover a lot today, so I'm not going to talk a lot about this particular bullet here, but you will hopefully see that this can work well for regular memory access patterns, assuming you can keep the hardware costs in check. But prefetching irregular access patterns is difficult and inaccurate and usually hardware intensive. And that's why prefetching irregular access patterns is a really good research topic today, because it's a hard problem. And you can see that this was initially implemented in IBM 36091 as an instruction prefetcher. And we will see what kind of instruction prefetcher they had. It is essentially a next line prefetcher, as we will see today. Multi-threading is another latency tolerance technique. So these two are latency hiding techniques. These two are latency tolerance techniques. I guess ignore the title here. Multi-threading, again, works well if there are multiple threads, but multi-threading is not beneficial if you want to improve single thread performance. And we've covered fine-grained multi-threading in digital design and computer architecture. I will have the link to that lecture in the next slide. And there have been works on improving single thread performance using multi-threading, maybe transparently to the programmer, sometimes with programmers' help. And this is an ongoing research effort. It's not an easy problem. This is actually a very difficult problem to do so. And it's not, as far as I know, there are not a lot of works that implement multi-threading to improve single thread performance. But if you're interested, I will have some pointers in the next slide. And out-of-order execution, clearly we covered this a lot in digital design and computer architecture. This is a latency tolerance techniques that improve single thread performance. And it can tolerate cache misses that cannot be prefetched. And clearly multi-threading doesn't work well for single thread performance. In fact, it reduces single thread performance, right? If you remember fine-grained multi-threading, that form of multi-threading reduces single thread performance because you're injecting into the pipeline a request from a thread only once every n cycles. Why? Because you don't want to check for dependencies. You don't want to do a branch prediction in that thread. And you just want different threads to cover the latency of instructions of each other, right? So out-of-order execution is a completely different latency tolerance technique. It basically looks ahead and speculatively executes instructions out of program order, but it finishes them in program order, clearly. And as a result, it can tolerate latency if there are not that many dependencies in the program, if you can actually get to independent instructions to execute in the presence of dependence chains. But it also requires extensive hardware resources for tolerating long latencies. If you have latencies on the order of 500 cycles, like we've discussed, you need very large buffers, very large register files to tolerate the latencies. And clearly, all of these topics are actually good research topics today, even though they have been researched for more than 50, 55, almost 60 years in some cases. There's still a lot of interesting things to do in this area if you have the creativity and ambition to do so. Okay, so clearly we've covered a lot of these caching. Some of these are digital design and computer architecture lectures. Some of these are earlier incarnations of this course. And this course has evolved also, so we don't cover as much caching in this course, as you can see. But if you're interested in some advanced cache management techniques, you can take a look at an earlier incarnation of this course. today we're going to cover prefetching, and there are a bunch of lectures. If you're interested in multi-threading, you can take a look at over here. And out-of-order execution and rendered execution, hopefully those of you who've taken digital design and computer architecture know very well about out-of-order execution, and you have an idea of run-ahead execution by now. And we're going to touch upon it today because it's really a prefetching technique. Even though I classified under latency tolerance, you could actually classify it in both places over here. Okay, so let's jump into prefetching then. So this is the outline of prefetching lectures. If we cannot finish it today, we'll probably continue tomorrow, although I'm not sure. Let's see. Basically, we're going to cover why we will prefetch, why could it or does it work, and we're going to cover the 4 questions in prefetching: what, when, where, and how. And then we're going to talk about software methods, and then hardware methods, and then hardware-software cooperative methods. Usually, execution-based prefetchers are hardware-software cooperative, but not necessarily also. And we're going to touch upon prefetching performance in between, somewhere over here. Talk about coverage, accuracy, and timeliness, 3 metrics to evaluate a prefetcher, plus side effects of prefetching, which is bandwidth consumption and cache pollution. So prefetching can actually reduce performance also if you do not do it well, just like caching can reduce performance, like we've discussed, right? And then we're going to talk about throttling prefetchers, which is orthogonal to all of these topics. I think we're going to talk about it earlier, actually, not somewhere in between. And then if we get to it, we're going to talk about issues in multi-core. So hopefully that sounds like a good plan. As I said, keep in mind, we're going to talk about a lot of techniques, but there's still room for improvement in these techniques. And this is probably an area in processor design where there's the most room for improvement, in my opinion, at least, because we're still short of covering the latencies that the processors sees. As you can see in our earlier lectures, right? Processor stalls for more than 50% or around 50% of the time waiting for data to come back. If the prefetcher was perfectly prefetching things and bringing data before the processor needs, the processor wouldn't ever need to stall, right? Clearly, there's room for improvement. Of course, the difficulty may be high as well in terms of how to actually get the data the processor needs before the processor needs it. Okay, so these are some readings. I guess ignore the required and recommended over here. We're going to have readings that are required and suggest or bonus in the homeworks, as you will see. But these 2 papers that we're going to cover are seminal papers. This Juppy paper, for example, introduces the stream prefetchers. They also introduced a victim cache, which we didn't talk about, but it's an advanced caching technique. So you can see that's a 30-year-old paper. And these techniques are employed in a lot of processors today, actually. And we have some recommended papers that we're going to touch on also. Okay, so what is prefetching? The idea, as you already know, is to fetch the data before it's needed by the program. This is called prefetching because of that reason, or preloading in earlier works. Essentially, why do we do it? Because memory latency is high. If we can prefetch accurately and early enough, we can reduce or eliminate that latency for a given request or for all requests in the ideal case, clearly. And the big upside of prefetching compared to caching is essentially it can eliminate requests that you have never seen before. Right? Whereas caching fundamentally has to see an address at least once so that it can cache it, right? Prefetching can predict what it's going to see based on the past access patterns or address patterns of the program. As a result, it can eliminate the requests or addresses that you're going to see into the future that you've never seen before. So that's a huge, powerful part of prefetching that doesn't exist in caching. So from this respect, caching is more of a reactive technique, right? Whereas prefetching is a proactive technique. In caching, you reactively decide, oh, I fetched this address. Should I keep it around so that if I need it in the future, I don't need to fetch it again. So it's reacting to what has happened, and it's making a prediction based on that reactive technique. Whereas prefetching is looking into the future. I've seen these addresses before, so let me think about what am I going to see next. And if I can predict that accurately, then I'm going to bring it into the processor early enough. And if I predict it correctly, then I would eliminate a miss that I would otherwise have incurred. So prefetching and caching work well together in the sense that one is reactive and one is proactive. If prefetching cannot prefetch, caching can catch it. If caching cannot catch it, well, I guess it doesn't make sense for caching to not catch it. But if you have a conflict miss, for example, in a cache, then Prefetcher can actually proactively prefetch data early enough so that it can get rid of conflict misses as well as compulsory cache misses clearly. Okay. And can it eliminate all cache misses? I guess the answer I have given you already. Basically, it can potentially eliminate all cache misses actually. That's why it can be powerful. It can eliminate conflict misses also by prefetching accordingly. If you have a conflict in a set, if your prefetcher is intelligent, maybe it can adapt to those conflict patterns, and as a result can get the data. Okay, there's a question. Let me look at it. When you say eliminating a miss, you really mean eliminating the latency of a miss, right? You still pay the energy cost. Yeah, absolutely, absolutely. So I made the transition to the processor-centric thinking, let's say. Yes, when I say eliminating a miss, it's really from the processor's perspective. It's not from the main memory's perspective. You still need to have a memory request generated. You still need to schedule it in the memory controller. You still need to wait for the memory to do an activate, pre-charge, activate, read, pre-charge, whatever is needed to service that memory request. And that memory request data comes back to the memory controller, and then you need to transfer it through the interconnect back to the processor. So you need to pay all of that cost with prefetching. Of course, it depends on where your prefetcher sits. And we will talk about that also. It could sit in the processor core. It could sit in the L2 cache. It could sit in the last double cache, L4 cache. It could sit in the memory controller. So you still need to pay the cost of memory access. And clearly, we're not eliminating the energy cost over here. In fact, we may be increasing the energy cost if we're inaccurate in which addresses we prefetch. So that's a good point. Basically, right now, we're talking completely processor-centric as the current systems are. Okay. So basically, we can eliminate all cache misses from the processor's perspective. Capacity, conflict, compulsory. You can get rid of all of them, potentially, of course. In practice, it's difficult to get rid of all of them. So clearly, this involves predicting which address will be needed in the future. And prefetching algorithms differ in how they predict which address will be needed in the future. And we will see a lot of different prefetching algorithms. Some of them are actually quite creative, in my opinion. But none of them actually work for all workloads, basically. To foreshadow, there's no single prefetching algorithm that's good for all workloads. All of them are designed to predict different types of access patterns, let's say. And in the end, if you want to really be successful, either you combine different prefetchers or you use some different type of approach. But in the end, combining prefetchers is a good idea, as we will also see when we talk about run-ahead execution. Okay, so this works if programs have predictable misaddress patterns, of course, right? If the programs have completely random address patterns, predicting which address is going to be difficult. That's why execution-based prefetchers will be useful. Then you may actually pre-execute the program as opposed to trying to predict using some heuristics what address will come next. So execution-based prefetchers are very powerful because they execute part of the program as a prefetch engine, let's say, so that they can bring the data earlier before the main program actually needs it. So we will talk about that also. Okay, so prefetching is clearly a speculation technique, right? Because you do something before you know that you will need what you do, right? And that's the definition of speculation, basically. You speculate. Your speculation is defined as doing something before you know that you need to do that. Right? But the good thing in prefetching is a misprediction in prefetching doesn't affect correctness. I've already given the answer. Basically, prefetched data at a mispredicted address is simply not used, right? There's no need for state recovery in this case. Of course, we're not talking about potential security implications over here. So correctness here is defined from the architectural instruction set architecture perspective. Basically, you don't need to, let's assume that you don't have any security implications of this prefetching, then you don't need to do anything about a prefetched data item, right? You don't need to recover, basically. Contrast this with branch prediction that we discussed in digital design and computer architecture, right? Branch prediction, if you mispredicted a branch, you're on the wrong path. Basically, you're executing wrong instructions completely. You have to recover, meaning that you have some implications on correctness if you don't recover. If you don't recover, basically, you will never complete the program because you're on the wrong path, right? Or you will never complete the program correctly because you've done things that you should not have done, right? So from that perspective, it doesn't affect correctness. But of course, there may be security implications of bringing data into the cache that you're not supposed to bring, right? It may be that someone can inspect your cache using Meltdown and Spectre or similar techniques that have been developed afterwards, that are actually prefetching versions of these techniques, which we're not going to talk about in this course since we don't have time, but it's good to think about those also when you're doing prefetching. They may actually lead to side channels that someone can exploit somehow, right? If they know how your prefetching algorithm operates, they can actually fool the prefetching algorithm to bring the data that they want into the cache, and they may somehow infer what that data is by taking advantage of the fact that you're executing together with some other application that's bringing the data. Okay, so hopefully this is interesting, but we're not going to talk about it. But the key takeaway from the slide is there's no need for state recovery because it doesn't affect your correctness from an architectural perspective. Okay, this is in contrast to branch misprediction or value misprediction. Value prediction is another technique that could be employed in systems. You predict the value or outcome of an instruction, data value of an instruction. And if you're wrong, then you need to recover because some other instruction have sourced that value potentially, right? Okay, so let's talk about some basics of prefetching. So in modern systems, prefetching is actually done in cache block granularity, usually. That's true for memory accesses, right? We've discussed that whenever you do a memory access, you usually do it in the cache block granularity because you're bringing data into the caches. I mean, that's not always the case, but especially with uncacheable data, actually, you can do a memory access to an 8-byte, for example, 8 bytes as opposed to 64 bytes. But prefetching is there to prefetch data for the program. It's usually done in cache block granularity. So we're going to talk mainly about cache block granularity in the rest of this lecture and in future lectures also. But keep in mind that it doesn't have to be done at the cache block granularity. Okay, this also gives you an idea of how caches are so well integrated into the systems. People are thinking about cache blocks as opposed to individual bytes, for example. Prefetching is a technique that can reduce both miss rate, cache miss rate, and cache miss latency, again, from the processor cache perspective. And it can be done by a hardware, compiler, or programmer, basically hardware or software, or in a cooperative manner, as we will also discuss. Okay, this is one example of how hardware prefetcher fits into the memory system. This is my Xfig drawing from maybe 14, 15 years ago in a paper that we wrote about prefetching, essentially. But you can see that this is a modern system at the time. Today, modern systems are more sophisticated. You have L3, L4 caches, etc. And you have the memory control on chip actually today. At the time we wrote this work, it was off chip, most of them. But okay, never mind. Most of the processor-centric systems are similar. But this is one example of how a hardware prefetcher fits into the memory system. So in this case, the hardware prefetcher, for example, is looking at L2 access stream and basically sees whatever is requested by this particular processor core from the L2. And basically can train its tables, let's say, to check, to recognize patterns, let's say. Let's say the processor is requesting cache block A, and then A+1, and then A+2, and then A+3. And then the hardware prefetcher says, oh, I see a pattern here. I always request +1. So I'm going to start requesting some future addresses in this stream, let's say. I'm going to start requesting, for example, A+8, A+9, A+10, in the anticipation that the processor will get there. So you could do that clearly, right? It also looks at the L2 demand misses, like what are the misses coming out of the L2 cache. And sometimes it actually creates its tables, table entries or monitoring table entries using this L2 demand misses. We will talk about some prefetchers that do that. That way you preserve entries in your stream prefetcher, for example. You don't need to create table entries for things that hit in the cache. but you really care about what misses in the cache because that's where the large latency comes from. And as a result, you can actually train the tables using hits, but you can create the tables using the misses over here. And then when you generate requests, you can generate the request. So let's assume that you see a stream, I don't know, address A+3, A+8, A+13, A+18. So that's a +5 stride, right? +5 in terms of cache blocks. So you basically figured out in your tables that you have a stride of +5, and then you basically generate prefetches, A+23, A+28, A+33, A+38, put them into the prefetch request queue, and then you basically send it to the L2 cache. And again, this is a design choice. Putting it into the L2 request queue might be a good idea. Some prefetchers directly put it over here. But of course, the downside is if it's already in the L2 cache, you have a problem, right? You're generating another request for no reason because A+23 is already in the L2 cache, right? So you need to be careful in terms of what request you send, because if you don't check the cache and send the request into the main memory, then you may be wasting bandwidth. Actually, you are wasting bandwidth. And as your fellow student mentioned, you're wasting energy as well. So you need to be very careful. You don't want to send the prefetch request into the memory system unnecessarily. Clearly, you don't want to send a prefetch request to the memory system if you have it in the caches, and you also don't want to send a memory request that's not going to be needed by the processor. And the art and science in prefetching is really balancing all of those. And we will see that there's a fundamental trade-off between coverage and accuracy in prefetching. Accuracy means, are the prefetches you're sending out accurate, meaning are they going to be needed by the processor? We're going to define it more formally later on. And the more accurate your prefetches are, clearly the less bandwidth and less energy you're wasting. But the more accurate your prefetches are, usually the less coverage you have. Coverage means how many of the cache misses the processor sees are just eliminated now because you have a prefetcher. So if you want to increase your coverage, if you want to eliminate your cache misses, you want to be more aggressive. And when you're more aggressive, you fundamentally become less accurate. So there's a trade-off between coverage and accuracy. And modern prefetchers actually have difficulty improving both at the same time, clearly. And we will also see some other dimensions of prefetching, like timeliness, in a little bit. You could potentially improve both at the same time, but you need to be very careful. Like you need to incorporate throttling mechanisms into your prefetcher, as we will also discuss. But this is just to give you an idea of where the prefetcher sits. In modern systems, actually, prefetchers sit all over the place. There may be a prefetcher in the L2 cache. There may be another prefetcher in the last level cache. There may be a prefetcher in the L1 cache. There may be a prefetcher in the memory controller, and they may need to coordinate with each other. That may be a difficult problem, of course, to coordinate with each other as well. So keep that in mind. So this problem becomes interesting and complex at the same time. Okay, so now let's talk about, regardless of where the prefetcher sits, regardless of whether it's software or hardware, regardless of whoever designs it, you have to answer 4 questions whenever you design a prefetcher, basically. And these are what, when, where, and how. The first one, what addresses do you prefetch? Essentially, what's the algorithm you use to decide for your address generator or address predictor, let's say. We're going to talk about that. We're going to talk about each of them actually very quickly, and then we're going to cover some prefetchers that answer these questions in different ways, let's say. When means, when do you initiate a prefetch request? Immediately, and also how many do you initiate at a given time? It's good to think about this question also, because if you initiate it too early, then you may lose performance because you may actually kick out from the cache or kick out from your prefetch buffer something useful. If you initiate it too late, then you may actually not cover the latency from the processor's perspective, right? Where do you place the prefetch data? We will see different options for this. Caches is actually the predominant option today that's used in existing systems. And then how is basically, how do you do it at a higher level? Do you do it at the software? Do you do it at the hardware level? Do you do it execution-based? Do you do it cooperatively? Do you do it as a combination of these things? How do you coordinate between different prefetchers? So how actually covers a lot of design space that's not covered by what, when, and where overall. Okay, so let's talk about these different questions. These are questions, but also challenges. I mean, all of the prefetchers actually have to answer it. But if you want to do a good job, it's a challenging thing to answer overall. So what actually is the question of what addresses do you prefetch? And this is important clearly because you don't want to prefetch useless data because that wastes resources, that wastes memory bandwidth, that wastes cache or prefetch buffer space that could have been utilized for something useful like demand requests or other useful prefetch requests. Clearly that wastes energy consumption. And all of these resources that are wasted could otherwise be utilized by demand requests or more accurate prefetch requests. So basically, you're wasting resources for someone else overall, or some other core's request, right? This core may be doing useless prefetching, but some other core may demand or may need the memory bandwidth, right? So we've seen this in the interference case. Whenever you're doing prefetching, interference actually increases. If we have time, we will talk about prefetching issues in multi-core. And whenever you have aggressive prefetchers in multi-core systems, the interference and quality of service issues become exacerbated. So you need to be even more careful in how you design the quality of service mechanisms. Okay, so accurate prediction of addresses to prefetch is important, as I mentioned. And this is the formal definition of prefetch accuracy, basically. Prefetch accuracy is defined as how many prefetches that you sent are used by the processor divided by how many prefetches did you send for a given prefetcher, for a given prefetch algorithm, let's say. Okay, so ideally you would like to be at a high point over here, 90%, 80%, but we will see that getting to that point is not that easy also. Okay, so the question is, of course, in this algorithm is how do we know what to prefetch? This is the prefetching algorithm now. You can predict based on past access patterns. That's one option. You can use the compiler's knowledge of data structures. That's one other option, as we will also see. And this is really the prefetching algorithm. And prefetching algorithm determines what to prefetch. And we will see a bunch of different algorithms in this lecture. We will focus on the what of prefetching quite a bit, because this is really the really interesting part. The other parts you can handle similarly in different prefetchers, perhaps. Of course, you may need to customize it depending on the prefetching algorithm. But prefetching algorithm is really where creativity comes in a lot, in my opinion. Okay, when to prefetch is important. Clearly, when basically it specifies when do you initiate a prefetch request. When does the prefetcher initiate a prefetch request? And as we discussed briefly, prefetching too early may be dangerous because prefetch data may not be used before it's evicted from the storage that is put into from the cache or the prefetch buffer, as we will discuss. Prefetching too late is also not good because you may not hide the whole memory latency. So you prefetch in cycle n, and in cycle n+1, the processor needs it. And the memory latency is 500 cycles. Your prefetcher is essentially useless in that case. Even though it started technically before the processor needed it, it didn't really cover the whole memory latency, right? It covered one cycle out of 500 cycles, which is practically nothing, right? So that's why when to initiate a prefetch request is important. And time, this is really related to the timeliness of a prefetch request. Basically, when a data item is prefetched, affects the timeliness of the prefetcher. And timeliness can be defined in multiple ways. I'm not going to go into these multiple definitions, but one definition could be a strict definition, right? Which is how many requests that I have sent that were used by the processor, and how many of them were actually in the cache when they were used by the processor. So you take the ratio of the second one that I said to the first one, how many of the useful prefetch requests were in the cache when I needed them by the processor, divided by how many useful prefetch requests that I sent. So that's one definition of timeliness. But of course, this is a very strict definition. It doesn't take into account the latency that may have been bridged. Basically, it says if it's in the cache, it's timely. If it's not in the cache, it's not timely. It's a binary, black and white definition of timeliness. Whereas the world is not black and white, right? It could be that you requested the prefetch. It's not perfectly timely. It's not going to be in the cache by the time the processor needs it, but it covers some of the latency, maybe let's say half of the latency, right? Okay, so a more less black and white definition of timeliness is how many cycles did it take for me to complete the useful prefetch request. Here we're really thinking about useful ones. Useless ones we don't care because clearly they're not timely. they're useless to begin with. So they're actually not considered in timeliness equations. But how many cycles did it take for me to actually finish the useful prefetch request? And how many of those cycles were covered by the prefetcher? Basically, the processor didn't need that request. So for example, if it takes 500 cycles to prefetch the data and the processor needs the data 300 cycles after the prefetch started, you covered 300 cycles out of 500 cycles. So your timeliness could be considered as 60%, let's say. But of course, these metrics are actually not so easy to quantify, especially when you have overlapping of requests, etc. We're not going to quantify it exactly, but you can look at the papers that talk about timeliness in terms of how they quantify it exactly. But overall, hopefully this gives you an idea, a notion of timeliness. A prefetcher can be made more timely by making it more aggressive, by trying to stay far ahead of the processor's access stream if you're doing hardware prefetching. Basically, if the hardware detected that you have a stride of 1, let's say A plus 1, A plus 2, A plus 3, A plus 4, A plus 5, the prefetcher can say, oh, okay, I'm going to skip ahead. I'm going to start prefetching A plus 20, A plus 21, A plus 22, A plus 23, in the anticipation that processor will have all of those requests in the cache by the time it actually needs them. So you can make things more aggressive by actually prefetching more or further into the future. But of course, this could reduce your accuracy, as we discussed, right? Because the processor may actually never get to A plus 20. Or if you're doing software-based prefetching, you can move the prefetch instructions earlier in the code, as we will see also. Okay, the third challenge in prefetching is, third question and challenge in prefetching is where? Where do you place the prefetch data? And usually there are two options. Today, you usually put it in the cache or in a separate prefetch buffer. In the cache, the design is simple. There's no need for separate buffers, clearly. And this is good. There's only a single point of entry, potentially, or the processor needs to check only a single place, let's say just the cache, right? But the downside is you can evict useful demand data if you're actually sharing the prefetches, sharing the cache between prefetches and demands, right? And that's unfortunately the case in many systems today. But because of simplicity, this is the preferred place to prefetch the data. But there are systems that were designed to prefetch data into separate data storage called prefetch buffers. This is a separate storage that's just used for prefetches. Clearly, now the demand data is protected by prefetches, no cache pollution. If you prefetch something useful or useless, you're not going to evict demand data that may be useful. But of course, the downside of having a separate buffer is now you have a more complex memory system design, right? Now, there are many questions here now. Where do you place the prefetch buffer? Do you place it next to the L1 cache, next to the L2 cache? How do you size it? How big should it be? I'm just jumping around with these questions because you need to answer all of these questions concurrently, actually. When do you access the prefetch buffer? Do you access it in parallel or in serial with the L1 cache, for example, if you decided to place it with the L1 cache? Because if you access it in serial with the L1 cache, you're actually increasing your latency. If you access it in parallel with the L1 cache, you may not be increasing the latency. You may get a hit in the prefetch buffer whenever you get a miss in the L1 cache, but concurrent access is always difficult. You may actually have useless accesses. When do you move the data from the prefetch buffer into the cache? Usually when you get a hit in the prefetch buffer, then it makes sense to move the data into the cache, but you don't have to, again. So now you have a whole lot of design choices that you need to make when you have another buffer into the system. How do you size it? In fact, if you have an aggressive prefetcher, you need very large size prefetch buffers, almost as large as L1 cache. In fact, sometimes even larger than L1 cache. And the prefetcher feedback directed prefetching paper that we will talk about shows that actually, and says that prefetch buffers is probably not a good idea with aggressive prefetchers. And also there's also one more problem. You prefetch the data. If some processor modifies it, you still need to keep the buffer coherent. So this increases the headache in terms of cache coherence in your system. We will hopefully talk about cache coherence in a lecture very soon. But it's not just about cache coherence. It's really about data coherence. Wherever you store data, if that data has the possibility to be modified by some other processor after you fetched it, then you need to keep that buffer coherent. This is true for prefetch buffers. This is true for any buffer where you buffer data into in the processor potentially. So basically, you need to be careful in terms of buffering data because it has implications on cache coherence, right? Because somebody else may modify a copy of the data that exists somewhere else, right? And you need to be aware of that. Okay, so clearly a separate prefetch buffer, it has advantages, but it also has disadvantages. And usually these disadvantages outweigh the advantages in especially aggressive prefetchers. And if you're interested, you can take a look at the feedback-directed prefetching paper that talks about this. And as a result, modern systems place prefetch data into the cache. And you can see many, many examples. I've stopped enumerating them, as you can see over here, because as far as I know, most modern systems, actually all modern systems that I know, put the prefetch data into the cache. Sometimes they protect, sometimes they put the prefetch data, for example, into only the least recently used position in the cache so that they don't evict potentially high value data items. And we will, if you have time, we will discuss the implications of that also. That may be good for protecting demands, but that may be bad for aggressive prefetchers again. An aggressive prefetcher may actually need more space than the LRU positions in the cache. Okay. And the last question in prefetching is where, basically. Where is different from this where. Well, I guess it's not the last question, sorry. There's a different form of where, I should say. One is where do you place the prefetch data, and the other is which level of cache to prefetch into, assuming you've decided to prefetch data into your caches. And there are many questions over here for which I'm not going to go into a lot of trade-offs. Clearly, you can imagine many trade-offs. Do you prefetch from memory to L1? Do you prefetch from memory to L2 directly? Do you prefetch from both memory to both of them? There are advantages and disadvantages. Clearly, if you have a very aggressive prefetcher, if you're prefetching directly from memory to L1, L1 size may not be enough. Again, so many prefetchers today prefetch into L2, but that's not all prefetchers prefetch from memory to L1. Sometimes you prefetch from L2 to L1. There may be a separate prefetcher between levels, and you can imagine that this generalizes to many levels. So this can get complicated, as I mentioned when I showed you the picture of where potentially a modern hardware prefetcher fits in the system. And then there's another level of where, which I alluded to earlier, which is where do you place the prefetch data in the cache? Okay, do we treat prefetch blocks the same as demand fetch blocks? And as I mentioned, there are some processors that place the data into the LRU position. HP Precision Architecture 7, for example, was an example. There are some existing processors that employ proprietary algorithms to decide where do you put a prefetch blocks. It's not just the LRU position, but slightly more intelligent algorithms than that. As we will see you'll see some glimpse of those algorithms when we discuss feedback-directed prefetching, which basically tries to intelligently decide which position in the cache a prefetch should go into. Should it go into the MRU position, some middle level position, or LRU position? You can also decide, oh, I'm not going to put it into the cache, right? I'm going to put it into the next level of the cache if you can do a good prediction. Okay, prefetch blocks are not known to be needed, clearly. That's why you're doing prefetching. With least recently used, the demand block is placed into the MRU position, basically. So basically, if you put a prefetch in the least recently used position, you don't displace a demand block into the MRU position, right? You're displacing, assuming least recently used policy holds in caches and it works well. That's a big assumption also, as you know. And not all access patterns benefit from least recently used policy. Then you're not evicting the predicted most important data into your cache by prefetching data into the most recently used position. Okay, and then the next question is, do we skew the replacement policy such that it favors the demand fetch blocks? For example, place all prefetches into the LRU position in a way. And maybe the answer is yes in some cases, but I think existing algorithms are more sophisticated, as we will see in the feedback-directed prefetching paper. Okay, there's another form of where, actually. So where is actually a big topic, which is where to place the hardware prefetcher. We've already discussed this kind of in one of the wheres, but I think it's also important to discuss it separately. Where do you place the hardware prefetcher inside the hierarchy? In other words, what access patterns does the prefetcher see? How do you connect the prefetcher in terms of what it can observe. If you do, it does actually observe all of the L1 hits and misses, which is L1 accesses. In that case, it has a complete picture of the L1 stream, access stream of the processor. So it may do a better prediction, but the downside is it's too much potentially, right? If the L1 cache is good at filtering out most of the requests, then why do you really care about L1 hits? That's a good question to answer. And you may not care actually, because they're going to hit in the L1 anyway. That, as a result, many prefetchers look at L1 misses. Many prefetchers also look at L2 misses for the same reason. L1 misses if the basically if the L2 hits most of the time, maybe you don't care, right? So the prefetcher that I showed you was created entries with L2 misses, but then it was trained on L2 hits, if you remember. Basically, it didn't miss the L2 access pattern, but it created tracking entries only when you get an L2 miss. We will talk about this in a little bit. So basically, it didn't. If things were hitting in L2, it didn't need to generate prefetches. But if things start missing in L2, it started creating. It started tracking access patterns, and then it started creating prefetch requests. Okay, you can imagine more things clearly. So seeing a more complete access pattern clearly potentially gives you a better accuracy and coverage in prefetching. Not always if you're not careful, but now the prefetcher needs to examine more requests. So it may be bandwidth intensive, more portions to the prefetcher, and sometimes if you see too much, you may not be able to actually discern the really important accesses, right? So that's also important. Seeing too much is not always good in prefetching. Okay, feel free to ask any questions. We're going to cover examples of this later on as well. But if you think there are questions that we need to clarify, feel free to ask. Okay, so this is the last point. That was a long coverage of where, especially. We talked about what, when, where. And the last one is how, basically. So how really determines a lot of the other things also. This is a question of where do you do the, I don't want to call it where again, but how exactly do you do the prefetching? Do you do it in software? Do you do it in hardware? Do you do it in a cooperative manner? Do you do it execution-based? Again, execution-based can be software or hardware, but it's a special mechanism. That's why I put it separately over here. But let's take a look at some examples of it. Software prefetching. In this case, the instruction set architecture provides prefetch instructions, and most existing architectures actually do. And the programmer or compiler inserts these prefetch instructions, which require some effort, clearly. And usually this works very well for irregular access patterns, as we will see. Hardware prefetching, on the other hand, is transparent, or transparent to software. Hardware monitors processor access patterns, and it either memorizes or finds in some other way finds patterns or strides, and generates prefetch addresses automatically, transparently to the software. Clearly, you can see both of them working together, right? Hardware recognizing some accesses and being guided by software in some way, or the software telling hardware, look, this is a place maybe you should be looking for monitoring accesses. These other things that I can handle, but these things I cannot handle because they're not regular. So please monitor these for me. Or the software can tell you, hardware, this is the stride over here, right? This is the expected stride that I have. So clearly these can collaborate with each other and become more hardware-software cooperative, which we're not going to talk about as much, but there are proposals that work that way. And I think those proposals are certainly interesting because they can be more powerful than hardware or software alone. Execution-based prefetchers are a different beast. They can be software or hardware or cooperative again. But here, the key distinguishing characteristic is you're using a thread to execute, and you're executing it to prefetch data for the main program. And we're going to talk about how to create this thread. This thread can be created by the software and the programmer, or done in hardware or cooperatively again. And this thread is actually, the sole purpose of this thread is to prefetch for the main program. So you're the programmer, you write the main program, and you say, okay, I'm going to put some little threads that just prefetch for the main program. And I'm going to attach them to the main program. And whenever main program reaches this instruction, I'm going to fork that thread. Okay, so as a programmer, you can do this if you have support in the instruction set architecture to do this clearly. Of course, it requires programmer effort, but if you know what you're doing, this could be very, very powerful, right? You could actually prefetch very irregular access patterns. For example, you're doing a lot of linked list traversals. You're doing a lot of hash table lookups, for example, right? if you have a single threaded program, whenever you do a hash table lookup, in each hash table bucket, let's say you have a linked list, you need to do a linked list traversal. And you don't know when the linked list ends. So you basically write code such that you traverse the linked list. Okay. But if you actually have the, meaning that it's very difficult to prefetch for this program, as we will see. If you actually had the opportunity to write a thread that's completely speculative, the whole purpose of this is to just prefetch data, you could also say, okay, I'm going to also create a thread that's going to execute into the future and get some future input or something, let's say. And it's going to access some other bucket in the hash table because the future input is different, clearly. And it's going to prefetch what happens over there. And whenever my main program actually gets to that bucket in the hash table, the linked list entries are already in my cache. Right? So you could actually easily do that as a programmer. A compiler can also do this if it's aware of the data structures and when it can do that. So execution-based prefetchers can be very powerful, actually. Run-ahead execution is actually another example of execution-based prefetcher, as we will also see. Basically, we saw the idea of run-ahead execution. Whenever you get to a long latency cache miss, whenever the window becomes full in an out-of-order execution engine, you checkpoint the architectural state and you keep executing the program. So that you keep executing the program speculatively because you're not going to finish the instructions. The purpose of that execution is just prefetch instructions into the caches. Now I can think of that keep executing the program part, the run-ahead mode, as a separate thread. It is a separate thread, actually, because you checkpointed the architectural state that you're going to go back into. This speculative thread that you're executing is, yes, it is the program that you have designed. It's the main program, but you're executing in a speculative fashion. So you're really executing the main program for prefetching for itself over there. So it's an execution-based prefetcher in the end. And there are other execution-based prefetchers that are also interesting that we will talk about. But again, you can see that this could be done in software, purely hardware like run-ahead, and in a cooperative manner as well. So the how part is also very, very interesting, as you can see, because this also is a place where you can exercise your creativity. And clearly, you're bound by different trade-offs depending on how you do the prefetching. Okay, so now we've covered those 4 questions, right? Now let's take a look at different types of algorithms or different types of designs that answer these questions differently. We're going to especially focus on what and how in these designs because those are the really interesting parts. Clearly, when and where are applicable to all of the prefetchers, but when and where you can answer these questions separately from what and how as well. Okay. So let's talk about software prefetching. And software prefetching is actually very interesting because some of the initial papers that were also published in 1990 by Ken Kennedy's group, for example, in Rice, were maybe ahead of this paper. I believe it was 1991, actually. I will provide that paper. It was in, I believe it was in PLDI, Programming Language Design and Implementation. It was a pure software prefetching algorithm. And they basically showed negative results. They said that this doesn't work in the programs they examined. And the idea was very similar to this Maury paper that was published in SPLOS 1992, which made it work, essentially, and showed good results. But the first time the software prefetching was published, actually the paper is called Software Prefetching. If you search for it, you will find it. The results were negative, and they basically said this doesn't work. And I think there was a thesis. I think Porterfield's thesis was actually on that topic, and it was a negative result. It was actually very good compiler algorithms employed to try to do the prefetching in that case, but somehow they didn't get it to work. But later, Todd Maury did his PhD thesis on prefetching, also software prefetching, and basically this is a seminal paper that he published showing that you can design a compiler algorithm that can effectively reduce latencies experienced by the processor by using prefetch instructions. Essentially, the idea is very simple, but of course, this can be done by the programmer also, clearly. Either the compiler or the programmer places prefetch instructions into appropriate places in the code, such that the code does the prefetching of data, and hopefully before the data is really needed, the prefetch instructions brought the data into the cache or prefetch buffer, wherever you're doing it. So in this paper, the prefetch instructions prefetch data into the caches. And compiler or programmer can insert such instructions to the program. And the key innovation in this work was having a compiler algorithm that analyzes the program, analyze the cache misses, analyze the load instructions, analyze when you can do this, analyze it where to insert the instructions to do the prefetching. Okay, so let's take a look at some of these instructions. This is from x86 in one of the x86 instruction manuals. Clearly, you can see that there are different forms of prefetch. And these prefetch instructions are differ from each other in terms of where they place the data. You can see that their specifications microarchitecture dependent, but you can see, let's take a look at the description actually quickly. These are hint instructions, meaning the processor designers don't necessarily need to implement them. They could be treated as no-ops also because they're not affecting correctness, as you remember from prefetching. And they could actually violate what they promised over here potentially because they're not affecting correctness, right? So let's take a look at this. The description says, fetches the line of data from memory that contains a byte specified within the source operand to a location in the cache hierarchy specified by a locality hint. Locality hint is this T0, T1, T2, and NTA, and where NTA stands for non-temporal data. So T0, for example, puts the data into first or second level cache in the Pentium 3 processor, and in Pentium 4 and Intel processors to second level cache, not first. And clearly, this is microarchitecture dependent specification, right? Depending on the microarchitecture, your program behaves differently microarchitecturally. And you can see different instructions for different cache levels. If you want to put data into, if you don't want to put data into the second level cache, for example, in Pentium 3, you use the NTA. But NTA essentially is not good. Basically, the distinction is not there in Pentium 4 and Intel Xeon processors. Everybody, all of these instructions prefetch data into the second level cache. So this is an example of difficulty of specifying instructions that operate on microarchitectural data structures like caches, right? Basically, the hardware designs improved over time, and the architecture designer said, okay, maybe we will handle these prefetch instructions completely in hardware. So we prefetch data into the second level cache, and we don't give the option to the user, for the programmer or the compiler, to specify where to prefetch data. I mean, to begin with, they do not have a lot of freedom to specify it anyway, right? So temporal data, for example, this is data that's supposed to be used a lot, potentially. That's why the promise was we prefetch into first or second level cache. You can see that it's an or, right? Only with non-temporal data, you don't prefetch data into the second level cache in the Pentium 3 processor. So overall, I would call this a mess. Basically, there's no good way of specifying a hardware-software interface that operates on a microarchitectural structure, because that microarchitectural structure changes over time. And as a result, the definition of the microarchitectural behavior of the instructions changes over time. And this is a really great example of that. Now, the benefit is the programmer can still use these instructions and hope that the hardware does something, right? Hopefully something useful. But of course, this is dependent on the hardware designer in the end. The hardware designer, as I said, may drop these prefetch instructions, and that's not uncommon also. We've seen prefetch instructions dropped in some designs. If, for example, the memory bandwidth is oversubscribed, right? The hardware makes that dynamic decision. I don't have the bandwidth to actually, all of the buffers are full, let's say, and I have a prefetch request waiting from a prefetch instruction. Do I stall the processor, wait to insert this prefetch instruction into the buffers and stall the processor? Or do I drop the prefetch instructions and hopefully let them make the processor make some progress, enable the processor to make some progress to do some more adds, for example, assuming that adds are going to come? Well, processor designers usually say, I'm going to drop the prefetch instruction. Why? Because clearly this is optional. It's not required for correctness. And I have these add instructions are waiting that are not optional, right? Even though the prefetch instruction in the end may be very, very useful, much more important than the add instruction, right? But this is the disconnect between the hardware designer and clearly the software designer, because you have to make a choice at the hardware design, and hardware designer may trust themselves more than the software designer, right? But again, this is something that's not very easy to fix unless you have a better interface between hardware and software. Much more. This is an example of hints that are provided by the software again. But we've discussed some interfaces like virtual block interface, but also expressive memory previously, very briefly, that can express more about your memory regions. That could actually provide more information that enables the hardware designers to do a better choice potentially. Okay, there's one question. Given these problems, do you know if manual prefetching is often applied in high-performance software? So that's a great question. I think usually the answer is yes. Basically, the problems are there, yes, but usually if you design your software well, not all of your prefetchers will be dropped. Let me put it that way. Maybe some of them get dropped if you have very high bandwidth demands, but usually hardware designers try to respect these prefetch instructions. But when they're really constrained, they may actually say, okay, this instruction is optional, right? Usually these instructions are actually implemented nicely, especially prefetch instructions. So that's a good question, basically. In my opinion, the answer is yes. And I've seen a lot of works that employ software prefetching to their benefit. And whenever they do a good job, they can get a lot of benefit. But there may be some cases where they may not see the benefits, even though they've done the right job, because the system is overloaded for some reason, their memory request buffers, for example. Okay. So let's, okay, sure. So I can talk more about these prefetch instructions, but that would occupy the entire lecture. So let's move on. Other instruction set architectures also have their version of prefetch instructions. Alpha ISA, which is one of my favorite ISAs, which is dead at this point because Digital Equipment Corporation got bought by Compaq and then HP at some point. Basically, it died, but that ISA, whenever you load it, an instruction, whenever you do a load into register 31, that's essentially a prefetch request, because register 31 is hardwired to 0, right? So you don't need to have a special prefetch instruction, let's say, in that ISA, because you have a register that's hardwired to 0, right? Okay, so let's take a look at, assuming that you have these prefetch instructions, how do you do the software prefetching? So this is one example of how you do the software prefetching, right? So you have a nice array access, and clearly you have a predictable access pattern. You're adding arrays A and B in a nice predictable manner. You're streaming through these two different arrays, let's say, through each element. And assume that your cache block size is 8 elements in this case. What you're doing is we've added these prefetch macros that the programmer can use. These are also called pragmas. Programmer inserts these pragma instructions, prefetch instructions, which could get converted into one of these prefetch instructions by the compiler. And programmer says, basically, I'm going to prefetch the next elements before I do the operation on the first elements of the arrays. So that's one example, right? Clearly, this may work if the data of the prefetches come back before you access the next iteration, right? Or before you access the next cache line, let's say, which means there are 8 iterations before you access the next cache line, because we're assuming, let's say, 8-byte elements and 64-byte cache lines. Okay. So if you do this, and if you're able to get the data before you finish 8 iterations, that's great. Then in the next iteration, or in the next time you need a cache block, it's already in the cache. Okay, and you can actually do the prefetch instructions before the loop as well, so that even the first iteration doesn't incur cache misses, right? So you can have prefetch instructions earlier, which are not shown here, but this is the steady state. Okay, so this sounds good, right? And this is good because it can work for regular array-based access patterns, but there are some issues even with regular array-based access patterns that you need to solve. One of them is prefetch instructions take up processing and execution bandwidth. You need to fetch these instructions, so they don't come for free, if you will. You still need to fetch and execute them. You can drop them later on. You don't need to, for example, wait for their completion Otherwise, that would be bad, right? If the prefetch instructions blocked your instruction window, that would be bad because they would be like regular loads. You have to have some sort of difference between regular loads and prefetches, and the big difference is you can drop them. Drop them is a different word. You can basically issue the prefetch request, and after that, you can forget about the prefetch instruction, right? Okay, that's the good part. They should not stall your window, but they still take up processing and execution bandwidth. Okay, this is different from a hardware prefetcher, as we will see. A hardware prefetcher doesn't need to take up instruction fetch bandwidth, which may be important, for example. Okay, there's a question of how early do you prefetch? Determining this is difficult, clearly. Clearly, if you look over here, there are multiple things that you need to determine. First of all, where do you insert the prefetch instructions becomes an issue. How far ahead do you need to prefetch? Do you prefetch I+8, I+16, I+32? Do you prefetch all of them? The prefetch distance depends on hardware implementation also, right? So how much ahead you prefetch depends on the memory latency, for example, the cache size, and the time between loop iterations. So let me give you a quick example. If your memory latency is 500 cycles, and you can parallelize the access to AI and BI, these go to memory, let's say, if you get cache misses on that. You need to determine that also. Do you get cache misses on those? But assume that you get cache misses on every element access, every cache block access, I should say, 500 cycles. Your loop iteration takes, I don't know, let's say 10 cycles. Then you need to prefetch 50 iterations ahead, right? That doesn't sound very good, okay? You need to prefetch basically to cover 50 iterations. So that doesn't sound very good. Basically, you need to prefetch very early. So going too far back in code reduces accuracy because there may be branches in between, and there are branches in between. As you can see over here, it's a for loop, and there's a loop ending branch, right? If your n is not very large, you may actually be prefetching things that a lot of things that are useless, right? Now, even if your n is large, at the end of your loop or close to the end of your loop, you're prefetching things that are useless because some of the things that you bring are never going to be used by this loop at least, right? Because your prefetches go beyond the boundary of what the loop touches, right? Clearly, I+8 will not be touched if I is equal to n, right? Makes sense, right? Okay. And you may need special prefetch instruction in the ISA, as we discussed, but that's easy in general. As I said, Alpha does this cute trick where it uses a load instruction to register 31, treat as a prefetch. And Power EC has data cache block touch instruction. I like that name, actually. It touches a data cache block. That's it. It doesn't necessarily wait for that data cache block to come back. And you saw the prefetch instruction in the x86 ISA. So you may need to extend your instruction set architecture for this, but that's already done today. And it's not easy to do this for pointer-based data structures also, as we will see in a little bit. But everything I said is not, so it's already not easy to do for regular data structures. You need to be careful where you insert these prefetch instructions. And the key difficulty, I think, is really determining whether these requests will hit in the cache or not, because you're also implementing caching in your systems. If you have a cache, and if caching somehow cache things, adding a prefetch instruction that brings the data that's already in the cache is not good, clearly. Now, the things become even worse if you already have a hardware prefetcher. If somebody implement a hardware prefetcher in your system, and if it's not turned off, and if it's also operating, well, now you're prefetching in software and you're prefetching in hardware, and your effort in software may be useless, right? Now there's a danger basically here. So usually the earlier question was on people who write high performance software. Well, their job is not easy. Basically, they need to figure out whether the hardware prefetcher exists. Usually it does. And how to actually work with the hardware prefetcher while they're doing also software prefetching. So they actually really need to understand the guts of the hardware prefetcher, or they need to turn off the hardware prefetcher if that's possible, if a hook is provided to them to be able to do that, right? So basically, software prefetching today, software prefetching in the past was not easy. That's why the earliest paper did not really provide positive results, in my opinion, because it was not easy basically to do this. Because you need to take into account whether you're going to miss in the cache. You need to take into account how long the loop will execute. and where to insert the prefetches based on that. If you're inaccurate, or prefetches may not be timely, you may be late. You're taking up instruction bandwidth also at the same time, so it's not coming for free, any of this. So it's easy to lose performance. And it's easier to lose performance today, actually, when you're doing hardware prefetching. Okay. But with regular array-based structures, you may actually have a potential possibility to win if you really know what you're doing. Okay, so this is very interesting, clearly. And compiler algorithms have been advanced on this topic also, clearly, but we're not going to cover them. But I think a good compiler cannot replace a good programmer in the end. A good programmer usually knows what they're doing better. It's very difficult to replace the good programmer completely with a good compiler. Okay, so let's take a look at why this does not work for pointer-based data structures. So let me give you the example of this. So this is a simple linked list traversal. We're traversing this linked list, and clearly I'm not checking for some conditions that I'm supposed to check over here, if P is null, etc. Right? I'm ignoring all of that code that needs to be there. Otherwise, you get a segmentation fault over here. At least in C, you get a segmentation fault. But assume that you check all of those conditions, etc. Let's assume that you want to prefetch for one of the loops for the next iteration, let's say, for this iteration, for next iteration, let's say. To be able to prefetch for next iteration, you need to insert the prefetch instruction at the beginning of this iteration before you do work on P. You prefetch for P next, and then P becomes P next. Okay, so this is possible. Clearly, you can do it, assuming you don't get a null pointer exception. But you cover only one iteration, right? And you can do it today, actually. You can do it in your programs if you're interested in doing it. You'd better check for null conditions. But the prefetch instruction may be automatically checking for null conditions. So prefetch instruction, if it gets, for example, a 0 pointer dereference, null pointer dereference, hardware may decide to drop it. Usually prefetch instructions, you don't take exceptions on prefetch instructions because they're not supposed to affect correctness, right? If you get a null pointer dereference here, here, or here, then you're in trouble, basically. That's in your real program. But in your prefetch instruction, you may get a null pointer dereference and hardware may not flag it. Similarly with page faults, for example, usually page faults are not handled with prefetch instructions because prefetch instructions are supposed to be speculative and they're not supposed to affect correctness. This is debatable, of course, right? Because it's a part of the ISA also. You could actually decide to handle page faults, but usually they're not handled. TLB misses are sometimes handled, sometimes not handled in the implementations of prefetch instructions. Okay, but this is code that prefetches for the next iteration, which is possible. There's nothing wrong with this code other than the fact that we have not checked for the P equals to null over here. Well, I guess this is checking while P, so this is doing that check. But prefetch P next may not be checking for null, and we already covered that. Okay, but let's take a look at this. What if you want to what if you want to prefetch for 3 iterations ahead? Can you do this? P next, next, next. And the answer I would say is yes, you can do it, I guess, but this is useless, right? Why? Because for this prefetch to take effect, you need to do 3 load instructions. A load instruction for this iteration, a load instruction for the next iteration, a load instruction for the next iteration, and they're dependent on each other. These are instructions that are dependent on each other, so this next should wait for this next, and clearly this next should wait for this next. So it's a dependence chain, meaning that this prefetch instruction, if you really want to execute it, you have to stall at that point. And if you stall at that point, you have a problem because you're not doing work. And the goal of the prefetch instruction was to overlap the latency of the memory access with 3 other iterations, but you're not even doing work for this iteration. So you're back to square one, maybe even worse. So you cannot basically prefetch for more than 1 iteration ahead if you're doing pointer chasing like this. So this is code that is, well, which one is better is a moot question at this point because I already answered it. Basically, this one is probably worse over here, and maybe this doesn't make sense even because clearly you're going to wait for data and you don't want to do this overall. Basically, the takeaway is, yes, you can prefetch for 1 iteration ahead if you're doing pointer chasing, but and iterations ahead, you cannot do it with at least simple prefetch instructions. Now, as we will see later on, you can potentially launch a thread that does this. So you can say, let's fork a thread that does p next, so that I can prefetch for n iterations ahead. And that thread executes independently. It doesn't block this particular program thread. Then that you're back in business, meaning that makes sense. Whereas this doesn't make sense over here. Okay, so hopefully that's clear. So this is a difficult thing. So pure software prefetching without being execution-based cannot handle pointer-based data structures well, as you can see. So this is employed the result for regular accesses, like array accesses that you can predict the boundaries of. But if array accesses whose boundaries cannot be predicted, whose access patterns cannot be predicted, those are also not easy to analyze, especially at the compiler level. With programmer can potentially decide what to do with them, but compiler level is very difficult. Okay, so the good question, basically, can we have a hardware module that performs those prefetches of a list? Yeah, potentially, right? Now, essentially, you're talking about somewhat like an execution-based prefetcher, because the hardware module needs to do all of this, p next. And yes, you can potentially have that, and people have actually proposed that. Amir Roth, for example, he did his thesis, well, part of his thesis on prefetching, and I don't remember the name of the paper. It's very sad, but I'm happy to point you to some prefetchers that essentially take this and do it in hardware completely. Okay, so that's a very good point. But with just a single instruction, like we discussed, you cannot do it. Okay, very good. So the next question is, where should a compiler insert prefetches, right? And this is also a difficult question. Okay, I would be interested in those papers. Please remind me, maybe post something on Piazza, that'd be great. And I'm happy to provide those papers. Thanks. Okay, prefetch for every, so clearly prefetching for every load access is not good, like what we have done over here, potentially. You really want to prefetch for loads that are going to miss, because otherwise it's too bandwidth intensive, because you're consuming both memory bandwidth and execution bandwidth. Usually the software algorithms, including the programmers, profile the code and determine the loads that are likely to miss. These are sometimes called delinquent loads. In fact, some of the prefetching papers are called delinquent load prefetching. These are essentially loads that misbehave, meaning miss in the caches. Compiler essentially tries to prefetch for those loads. Now, whenever you're doing profiling at the compiler level or programmer level, you're always bound by how good your profiling input set is. If the profiling input set is not representative, meaning it doesn't reflect the execution input set of the program, then you may actually insert prefetch instructions that are not going to be useful. You may say, okay, these are going to miss in the cache, but when you're doing the real execution with real input sets, they're not going to miss in the cache. So that's too bad. You're reliant on profiling, right? Okay, there's also the question of how far ahead before the miss should the prefetch be inserted. Again, you usually profile and determine the probability of use for various prefetch distances from the miss. And again, what if the profile input set is not representative? And you usually need to insert a prefetch far in advance to cover hundreds of cycles of main memory latency. As a result, you get reduced accuracy because you need to raise early. You need to put your prefetch instructions early. And the prefetch instruction that's put early may never actually get be needed by the demand that is supposed to be prefetching for, because there may be enough branches that take the control flow somewhere else in the end. So you prefetch for this demand that you think you're going to execute, but you never get to that demand because the code goes some other way, right? So you need to be very careful, basically. So as a result, software prefetching, even though whenever it's employed and done correctly and nicely by someone who's an expert in both hardware and software, let me put it that way, it improves performance. Hardware prefetching is usually much easier in a general purpose manner. So that's why we're going to talk about hardware prefetching. But I think it's a good idea to stop right now and perhaps take a 13-minute break and come back at 14:45 so that we can continue with hardware prefetching methods. Okay, let's continue where we left off. So we already discussed software prefetching. So hopefully everybody remembers it. It was 15 minutes ago. Now we're going to switch to hardware prefetching. And I already described what this is, but essentially the idea is to have specialized hardware to observe, load and store access patterns and prefetch data based on this past access behavior that's observed. And it's a simple idea, clearly, but it's an idea that has many trade-offs also. And all of the processors that you're using today are using some sort of prefetcher, and some of the algorithms inside there are very sophisticated. We're not going to get into the most sophisticated algorithms, unfortunately. That requires one more lecture, but I'm going to point you to some papers related to that. So the upside of hardware prefetching, or pure hardware prefetching, is now you can tune it to system implementation, whereas software, you didn't have that choice, right? Basically, software somehow needed to know about all of these parameters in the microarchitecture and guess which instructions missed and hit. Whereas hardware, you have all that information, basically. You can feed instructions, you could feed access patterns to a particular specialized block, and that particular specialized block intelligently generates prefetch requests. So you can adapt to the memory latency, you can adapt to the memory bandwidth, you can adapt to how well you're doing in terms of timeliness, you can potentially adapt to how well you're doing in terms of coverage and accuracy, all of those metrics we have mentioned, but we will discuss even more. And on top of this, you don't waste instruction execution bandwidth. So this is a clear advantage over software prefetching. Somebody doesn't need to provide the instructions and nobody needs to execute instructions. This can all be happening concurrently while the processor is actually making progress, hopefully. Of course, the downside is now you need more hardware complexity to detect patterns. And in some cases, software can be more efficient, right? So this leads to hardware-software cooperative mechanisms that you can imagine, and we will briefly talk about, where the software provides the type of pattern and hardware actually tries to detect that type of pattern. That's also a possibility, as we will see. So the software-hardware cooperative mechanisms can actually do even better. But we will first start with pure hardware mechanisms to detect patterns. And the simplest pattern is called next line prefetchers. This is the simplest form of hardware prefetching. And basically, the idea is very simple. Always prefetch next and cache lines after demand access. So if the demand access goes to address A, you prefetch address A+1 to A+n, all of them. And again, you can decide to do it on a demand miss also, not just hits. Misses are usually better in general. They save prefetch requests and the corresponding bandwidth cost. This is called the next line prefetcher, or also called the next sequential prefetcher. This is simple to implement. No need for sophisticated pattern detection, clearly. You always guess that whenever you access address A, you're going to access address A1 plus n with some sort of locality, right? And this works well for sequential and streaming access patterns. For example, instructions are the ones who would benefit a lot from this, right? If you have, since instructions are executed in sequential order in the von Neumann model, you basically are expected to go to the next instruction unless you have a control flow change. Then, assuming that you don't have control flow changes, significant control flow changes at least, you basically keep accessing the next cache block and the cache block after that and the cache block after that, et cetera, et cetera. And as a result, next line prefetchers work well for instructions. Next line prefetchers work well for array accesses, for example. If you're streaming through an array, this makes sense, clearly. But they may not work very well for irregular access patterns, clearly. As I said, it can waste bandwidth in irregular access patterns. Let me give you some example patterns. Even with regular access patterns, actually, let's not even go into irregular access patterns, because let's assume that you're accessing memory randomly. Then if your access pattern is irregular and you're never touching address A1 plus, address A+1, let's say, assuming n is 1 here, you're very conservative, clearly, then all of your requests that are generated whenever you touch address A, address B, address C, address D, address E, that have nothing to do with each other, lead to useless demand requests, right? If you are completely irregular, meaning random access. So clearly that's not good. But even with regular patterns, you may actually run into problems. For example, if your access stride is 2, meaning you're always accessing the second cache block after the cache block you're currently accessing, meaning you're accessing address A plus 2, A plus 4, A plus 6, A plus 8, dot. And if your n is 1 in the prefetcher, you're always prefetching address A plus 1, and then address A plus 3, and then address A plus 5, whenever you get the next access, of course. Then you have a problem, basically. You're never prefetching accurately. You're always wasting bandwidth, right? So this is one example, clearly. And you can imagine many other examples. There's also the other question here. What if the program is traversing memory from higher to lower addresses? Why do plus? Why not do minus, for example? You access address A, access address A, and then A minus 1, A minus 2, A minus 3, A minus 4. So do you also prefetch the previous N cache lines? Well, now it becomes wasteful for sure, right? Because you may not be going both ways in your array, clearly, or whatever data structure that you're traversing at that point in time. So this becomes a bit unwieldy. So of course, now you become more clever and you say, okay, if I'm going positively, I do plus. If I'm going negatively, I do minus, meaning that you need to somehow detect what you're doing. And that will lead us to future prefetchers that try to detect these strides, that try to detect some locality in the prefetching. So next line prefetchers were an early attempt in the 1970s. They were first employed in IBM, actually, 36091 instruction prefetching mechanisms, but also later on in some other IBM systems. They worked well if the prefetch access patterns matched the program access patterns, clearly, but they wasted a lot of bandwidth and led to a performance loss sometimes if they didn't match. So you need more adaptive prefetching mechanisms to adapt to program access patterns, clearly, as you can imagine based on my last question over here. Okay, so people developed stride prefetchers after this, and stride prefetchers essentially are two kinds. These try to detect the difference between the current access and the prior access and determine a stride between that the processor is going through. So there are two kinds, as I said. One is instruction program based, program counter based, PC based, and the other is cache block address based. And we will discuss the differences between them. But this is the first paper that I know of that introduced the instruction based stride prefetcher. And the idea is this, basically, very simple. You record the distance between the memory addresses referenced by a load instruction, as well as the last address referenced by the load. So basically, you have the stride of the load, which is the memory distance between the memory address referenced by the load instruction. That's called the stride of the load, and the last address referenced by the load. And next time the same load instruction is fetched, you prefetch last address plus stride. So let me give you an example. If you're going through, for example, address A for the load, for a given load, address A plus 4, address A plus 8, clear, and then address A plus 12, clearly a human can say, oh, my stride is 4, right? Basically, you design machinery for this. The machinery is, as soon as you see address A, you start a tracking mechanism for that program counter. When you see address A plus 4, you say, okay, my stride is 4. And then you predict, I'm going to address I'm going to access address A plus 8 next time, which is last address plus stride. Makes sense, right? Assuming that your stride continues to be like that, you're golden. But if your stride is different, now let's say it starts to become A plus 5, A plus 4, and then you get A plus 5, and then you get A plus 8. Okay, you cover some of the addresses, but maybe you don't cover all of them. But if your stride changes, then you need to adapt to the stride. So you can adapt to the stride, actually, that's fine. But if you have multiple strides, this becomes difficult to detect with a single predictor. Okay, let me give you an example of instruction-based stride prefetching, very simple version of it. Basically, you have a table that keeps track of different load instruction program counters. You have the tag of the program counter, essentially. And for each program counter, you keep track of what is the last address that is referenced by the program counter and what is the last stride. And you may have some confidence value to decide, okay, I'm confident in the stride itself. Stride didn't change much in the last, I don't know, n executions, right? So this way you can actually easily keep track of your stride, because you basically subtract the current address or last address from the current address. That'll be your stride. And then you also compare that to the stored last stride, and then you determine your confidence, right? Okay, so it's relatively simple. But there are problems, there are issues with this. Even with this is a simple mechanism, it could potentially work. But one issue is how far can the prefetcher get ahead of the demand access stream, right? So that is an issue, basically. Basically, initiating the prefetch when the load is fetched the next time can be too late, because load will access the data cache soon after it's fetched, right? So you'll fetch the load. In 5 cycles, it may get to the data cache access stage in the pipeline. And if you have this prefetcher operating at the fetch stage, let's say, instruction fetch stage, you're already too late, right? Why? Because you will cover only 5 cycles out of 500 memory access cycles. That doesn't sound good. So you basically should not wait until you fetch the next instance of the load instruction. You should really start prefetching ahead. And there are multiple ways of doing that, basically. I will talk about the second version over here, prefetch ahead, basically. So you don't prefetch last address plus stride. You prefetch last address plus n times stride, for example. You're prefetching n instructions ahead this way. And in the steady state, you're prefetching always n instructions ahead. At the beginning, you may actually prefetch for last address plus stride, last address plus 2 times stride, last address plus 3 times stride, etc., to basically fill the pipeline, let's say, with prefetches that cover your latencies. But this is a good idea potentially, right? But if your n is too large, now you're becoming too aggressive. Potentially, the demand access stream will never get to n if n is too large, right? That's the issue over here. You can also generate multiple prefetches, meaning not just a last address plus n times stride, but last address plus n times stride, plus n plus 1 times stride, plus n plus 1 two times stride. So you basically predict ahead multiple iterations of this load instruction. And multiple prefetches clearly make the prefetches more timely, but they also make it more aggressive. And these folks, I'm not going to talk about this as much, but these folks, Chen and Baer, which is a seminal paper that introduced program counter-based stride prefetching, they also introduced what is called a look-ahead PC. They basically said, we want to be even more clever, let's say. We want to decouple the front end of the processor from the back end and basically run the front end faster, such that we can get to PCs earlier, meaning fetch engine doesn't need to be coupled to the backend engine, right? You could actually keep fetching the instructions while the backend is stalled, as long as you have a queue large enough to buffer the instructions. This is called a decoupled fetch engine. And it's not new to this paper, but it's employed in IBM processors for a really long time. For example, IBM mainframe processors. They earlier discovered that, okay, we're stalled by the backend because we're waiting for data, but we can at least keep the front end running. How do we keep the front end running? Basically, we keep fetching instructions, and we could potentially direct the fetch using branch predictor. Okay, as long as I have a buffer large enough to buffer instructions, the front end of the machine can run ahead of the back end of the machine. So these folks said that, oh, if I run ahead, run ahead is actually an overloaded term, but if I look ahead in my front end and I keep fetching instructions, I can actually find out, have a look ahead PC, and this program counter can be used to index my prefetcher table. And then I'm essentially looking ahead in the instruction stream while the backend is stalled. And that's the idea over here. And this is not a bad idea, except when backend is not stalled as much, this doesn't help. So this requires some stalling on the part of the backend. Whereas these other ones, prefetch ahead and generate multiple prefetches, doing them together will help, regardless of whether or not your backend is stalled at the moment, basically. Okay, so hopefully this is clear. It's a very simple idea, clearly. You detect strides, right? And it may work in some cases when your stride is regular, clearly, and if you can look ahead. And there are techniques to look ahead, as you can see over here. Now, let's take a look at another version of this. This is called cache block address-based stride prefetching. Basically, here you don't have anything to do with program counter. You don't base the prefetch decisions based on instructions. So the previous one exploits instruction level strides, instructions accessing address A plus N, A plus 2N, etc. Whereas some other instructions accessing address B, B plus M, B plus 2M, B plus 3M, etc. And you're distinguishing between them. But another approach is looking at just memory block addresses, not taking into account program counter. And that approach basically just looks at the memory block addresses issued by last level cache, let's say, and essentially detects strides. For example, you can have A plus N, A plus 2N, A plus 3N, and that could be detected by whatever address tag you have and the stride you have over here. If you get B, B plus M, B plus 2M, B plus 3M, that could be detected by another address tag because B clearly doesn't match A, right? That's the idea. So you can form the table based on the program counter or block address that you see. And you can still have control or confidence, meaning how many times you've seen N stride given an address tag A related to A, etc. And stream buffers, as we will discuss, are a special case of cache block address-based stride prefetching where N is equal to 1. Basically, you're streaming through memory, A plus 1, A plus 2, A plus 3, A plus 4. That's called streaming through memory. So stream is really, at least from the main memory perspective, is a memory stride of 1 cache block. We always talk about cache blocks in this case, but again, the idea is generally applicable. Even if you're looking at non-cache blocks, bytes, you can apply the ideas. Okay, so hopefully this is clear also. Let's talk about stream buffers. But the main benefit over here of cache block over program counter based is you can detect potential strides that happen due to multiple program counters, right? Whereas you cannot detect that with program counter based. When you look at program counters, you may not have a stride, but when you mix multiple program counters, they access memory in such a way that you can get streams, for example, or you can get some sort of striding behavior. Of course, there's a downside as well here, which is you cannot distinguish things easily based on program counter. Program counter is nice, but here, okay, one of the let's assume that you keep doing A plus N, A plus 2N, A plus 3N, etc. At some point, you get to a memory region that may also be being fetched by another address tag over here. So you start with A and B, and at some point they start overlapping with each other, right? That's possible. If A starts at some address A, B starts at some address B, and they keep increasing. And let's assume that B is ahead of A, far away of A, but A has a larger stride than B. At some point, these two things start generating similar addresses potentially, maybe the same addresses, and that becomes potentially an issue. So these prefetchers usually have ways of detecting duplicate entries in their address tags and removing these duplicate entries easily or hard ways. Okay, so that's a side issue that you may run into when you're doing cache block address-based prefetching, basically. Okay, so this is the stream buffers example. It's essentially a special case of cache block address-based stride prefetching where stride is 1, and you integrate your prefetcher into after the data cache, as you can see. And this is introduced by the seminal paper by Norm Juppy, who has worked on many, many things over his lifetime. In fact, he's the first author of Google TPU, for example, 27 years after this paper. Basically, the basic idea is what I just said earlier. You have stream buffers. Each stream buffer holds one stream of sequentially prefetched cache lines. Let's assume that stream starts at N. You have N, M plus 1, M plus 2, M plus 3, M plus 4, ... And then another stream that starts at X, X plus 1, X plus 2, X plus 3, ... And you may have some number of streams. And the reason you have many of these is so that you can distinguish between different streams. For example, if you have array A, B, C, D, E, and if you're adding all of those to each other, each of them will map to a different stream nicely, A, B, C, D, E, and maybe the result will go to F. Then you have 5 streams, right? And nicely, you're supposed to get the same cache block from each of them at the same time, right? If your program is operating adding A, B, C, D, E, well, A, B, C, D is 5. I don't know why I came up with that, but the result should go to F, and you have 6 streams clearly. Okay, so how does this work? Very quickly, on a load miss, the cache checks the head of all stream buffers for an address match. Let's say your address is X, the cache checks the head of the FIFO. Do I have X? If it has X, it pops the entry from the FIFO queue and updates the cache with the data. If not, it allocates a new stream buffer to the new misaddress, basically. And it may have to replace a stream buffer following the LRU policy as proposed in this paper. So it's very simple and rigid. And stream buffer FIFOs are continuously topped off, meaning you prefetch data into the FIFO with subsequent cache lines whenever there's room in the stream buffer and the bus is not busy. So there are a lot of interesting ideas over here. If you have room here, prefetch. Meaning, let's assume that you have X over here and prefetched address X plus 1, X plus 2, X plus 3. And if you have room for 5 more, let's say, prefetch X plus 4, X plus 5, X plus 6, X plus 7 when the bus is busy, when the bus is not busy. And do it in a nice manner in a round robin order if you have some other stream buffers that have the same property, meaning they have empty entries and you're using them for some definition of using that you determine dynamically, right? So this works nicely for the patterns that I mentioned. If you're accessing arrays in a regular streaming fashion and you have multiple streams, you distinguish between them clearly, nicely over here. And it works beautifully, actually. In fact, in that case, one questions the need for a cache also. Do you really need a cache? In fact, there's a work by Palacharla and Kessler in ISCA 1994 that talks about stream buffers as a secondary cache replacement. They replaced the secondary cache, L2 cache, very similarly to this work. And they basically said in workloads that have this sort of streaming behavior, we don't need an L2 cache. We just need stream buffers like this. And because all of your accesses go through the stream buffers. But of course, if your accesses don't go through the stream buffers, a cache may be beneficial, right? So that's the idea of stream buffers. And let's take a look at one stream buffer design over here from that paper. Basically, the CPU address coming from the data cache gets compared to the tag at the head of the stream buffer. And if it's a match, you get the data from the cache block and cache block goes into cache. Of course, it needs to be valid as well. That's what a match is, right? And then you move the top to the head of the stream buffer. So you need to actually have some management logic to keep track of what is the head of the stream buffer, what is the tail, etc. And then this is the prefetch address, which is the next address that is not in the stream buffer. And then you keep incrementing it. So it's a very simple design in the end. And the comparison is also simple because you're comparing to the address coming from the CPU only to the head of the stream buffer. And this is directly from the paper. You can see an example of 4 stream buffers over here. And I'm not going to go into the details of this, but you can see a very specialized design just for streaming +1. And you can imagine if you have 4 of these, this works nicely with a maximum of 4 arrays that you're streaming through. If you have a 5th one, well, too bad. Basically, you've overflown your system streaming buffers, and as a result, your system will not be as effective. So clearly, this design or this sort of prefetcher design is very much coupled with the access pattern that you have in the system. And how many stream buffers you need to design depends on how many of these access patterns, streaming access patterns you have going on concurrently. And later works actually made the stream buffer design more flexible in the sense that they got rid of the +1. They basically said we're going to predict what the stride will be in each of these buffers. So it looks more like a stride predictor, but maybe it's a simpler version of the stride predictor. This is called predictor directed stream buffers. You can find it. And you can actually make it less rigid compared to this. You can detect, actually many prefetchers today detect multiple strides. So they don't basically work on just detecting +2, +2, +2, +2, +2. They can detect 2 strides potentially, right? Your access pattern stream may be +2, +3, +2, +3, +2, +3. So let me give you an example. Actually, I like the +2, +8 version better. +2, +8, +2, +8. So the first access is to address A. The next address is to address A +2, and then address A +10. And then the next address is to address A +12, and then the address A +20. And then address A +22, address A +30. This could happen. This all depends on how you access your data structures, right? The smaller stride may be due to a field that you're accessing in a smaller data structure. The bigger stride may be due to going to the next element in your bigger data structure. So clearly this is possible. The smaller strides usually come from field accesses. The larger stride comes from going to the next bigger data structure object that you go into. So you may overall be going through objects in a sequential fashion, but each object is large, let's say 8 cache blocks. And from each object, you just need the second cache block and the object itself. So basically, and the header of the object itself. As a result, you can easily run into a situation where you have a stride of 2.8, 2.8, 2.8, 2.8, 2.8, 2.8 going. And existing prefetchers are designed to latch into this sort of patterns. This is called delta prefetchers, delta prefetching. We may get to that also in a little bit. But there are variations on stride prefetchers, but clearly they're more capable than stride prefetchers. And all of them are a variation on the stream buffer designs to begin with, which is this work. Okay, so hopefully that's clear. Let's talk about trade-offs in stride prefetching. I've already talked about a lot of this, but instruction-based stride prefetching versus cache block address-based stride prefetching. The latter, as I said, can exploit strides that can occur due to the interaction of multiple instructions, which I gave you an example of actually. The strides that may happen 2 plus 2 plus 8 plus 2 plus 8 can happen potentially due to multiple instructions, but you can have even more complex patterns. And the latter can more easily get further ahead of the processor access stream. You don't need a look ahead program counter, for example. You can more easily adjust the aggressiveness of the prefetcher if you're doing cache block address-based stride prefetching. This doesn't mean that instruction-based stride prefetching doesn't have advantages. It does have advantages. One is it's less hardware intensive, as many recent works also showed. And also you may get some sort of predictability potentially in program counter-based prefetching that you don't get out of cache block address-based stride prefetching. You may look at cache block-based stride-based prefetching and you don't find any good stride. Whereas if you just look at the instruction, you may find a good stride, right? That's also possible. It really depends on the access patterns in the end. But the latter is more hardware intensive, mainly because there are usually more data addresses, data blocks to monitor than instructions, because systems are much more data intensive compared to instruction intensive today. Okay, so now I'm going to move into more locality-based prefetchers. I'm not going to spend a whole lot of time on this one, but in many applications, access patterns are not perfectly strided. Some patterns look random to close by addresses. And the key question is, how do you capture such addresses? And this becomes much more difficult now because you don't have a stride and some patterns look random. How do you capture these? An example of locality-based stride prefetching is provided in this work that I'm going to cover in a different way. So I'm going to try to maybe talk about this prefetcher very quickly, even though the definition is on this slide. You can read, and it's also in many Intel patents, not just a slide. Okay, so let's take a look at this example. I hope folks are seeing me. Can you see the whiteboard? I guess you can, right?
Yes.
Okay, great. And I don't know why I cannot write on it, but I guess let's try. So basically, what we're talking about is something like this. You have address to access A, access to address A, and then you may access address A plus 2, and then you may access address A plus 5, and then you may access address A plus 4, and then you may access address A plus 10. So hopefully you get the idea. And then you may access address A plus 11, and then you may access address A plus 8, and then you may access address A plus 17, ... right? So this is the processor's access stream, but it's happening in an order that's very, I mean, that doesn't have any stride, as you can see, right? I just made it up, but I'm pretty sure this doesn't have any good stride to begin with. But basically, you can run into such situations. Why? Because programs are irregular. You may be accessing some data structure in different fields based on some branching control flow that you have over there in the program. So this happens actually in many programs. And a stream prefetcher doesn't work well. Well, it can potentially work well, actually, a stream prefetcher in this particular case, because we're accessing a lot of things in the stream. And you need to look ahead, of course, to be able to do this. A stride prefetcher doesn't work very well because it misses a lot of the accesses. It cannot latch onto a stride. But sometimes, even if a stream prefetcher can potentially prefetch, or a next line prefetcher can potentially prefetch, next n line prefetcher can potentially prefetch, all of these, it may be very bandwidth intensive. So what some processors do, Pentium 4 being one of them, Intel Pentium 4, they actually try to detect what happens, basically, and they use a locality-based prefetching technique. I call this a locality-based prefetcher for the lack of a definition of a term in existing prefetching literature. But the basic idea is, what happens is, whenever you get a miss, I don't know what's happening again. Well, I guess my pen died. Can I do it with my hand? I cannot do it with my hand. Oh, okay, I see. My pen didn't die, but something else happened. Well, okay, we're having a lot of technical issues here. Let me try to, maybe my computer died. Can you hear me?
Yes, we can hear you.
Okay, you can hear me, but I cannot do anything on my iPad. Maybe it's time to move from iPad. Okay, now I can do something. Okay, maybe it's my pen. But so I'm going to be relatively quick. Let's assume that you get a miss to address A. The processor has a miss to address A. The prefetcher creates a tracking table. Well, creates an entry in the tracking table that looks at address A. Okay, and then what it does is it monitors address accesses to somewhere in the vicinity of address A. Let's say address A minus 16, address A plus 16. Okay, next request goes to address A plus 5. That's good. So it's within this vicinity, A plus 16, A minus 16. And then it says, oh, maybe my direction, so it needs to record a direction. Maybe my direction is positive. And you can have confidence counters clearly. And then the next access is to address A plus 14. Now you have more confidence that your direction is positive and you're going in the positive direction. And then maybe the prefetcher at some point says, oh, I have 2 requests within this window. This is called a tracking window, at least the positive part of the tracking window. I have 2 requests within the window. So I have enough evidence that my direction is positive and the processor is doing something interesting. So let me start prefetching. And the prefetcher maybe decides to start prefetching. I don't know. It's a design choice, of course. Maybe it says, oh, I'm going to start prefetching from address A plus 5. Or it says, I'm going to prefetch everything within this window. That's aggressive, clearly. But it may be useful if you have the bandwidth. So it's possible. So there's a design choice as to what to prefetch at that point. So basically, that's the idea. You keep track of a tracking window where you keep track of locality of misses or accesses. You create a tracking entry on a miss in the tracking table, and you look at the plus and minus windows. And based on the accesses you get within that window, you train the prefetcher. You figure out the direction. And also you potentially figure out a stride. Usually you may not figure out a stride depending on the workload. And you start prefetching. And when you start prefetching, you have a design choice. What do you prefetch? And some of these prefetchers start by saying, okay, I'm going to prefetch from, let's say, everything from address A plus 8 to address A plus 16, and also a little bit further. And then later, I'm going to keep monitoring accesses. Let's say if I still get accesses to the tracking window, oh, that's good. That means I should prefetch a little bit more into the future. If I keep getting access to the tracking window, oh, maybe I should prefetch a little bit more into the future. If I keep getting access to the tracking window, I should prefetch a little bit more. And at some point, you move the tracking window to address A plus 8, to address A plus, I don't know, whatever, 24. And you monitor that tracking window. So what this prefetcher is trying to do is it's trying to adapt to the locality of accesses within a window. And it's trying to slide the window as the processor slides the demand access stream window. Right? So this is a prefetcher that's closer to what's employed in some of the state-of-the-art processors. And this is the basics, basically. And the paper that I mentioned earlier, which is our feedback-directed prefetching paper, talks about this prefetcher. Of course, existing versions of this prefetcher do a lot of other tricks. So clearly, they have confidence mechanisms to determine the direction. If the direction is negative, they also prefetch in the negative direction. They also have potential confidence mechanisms to detect a stride. So if they actually detect a stride, they go into a stride-based prefetching mode. They try to have throttling mechanisms based on available bandwidth. So they don't go as aggressive as issuing 8 prefetch requests or 2 prefetch requests later on. They basically adapt the number of prefetch requests they issue. They determine the window size dynamically also. So if they don't have a lot of bandwidth, for example, they reduce the window size. If they have a lot of bandwidth, they increase the window size. If there is not a lot of memory bandwidth, they they reduce the window size because they become less aggressive that way. And they may actually go both directions potentially. And as I said, they have mechanisms to do it for multiple possible windows, tracking windows. And they have mechanisms to actually eliminate overlapping windows potentially, because at some point, as I mentioned earlier, this window starts overlapping with another window B because they happen to be in the same memory address space. And these prefetchers try to detect that, and they try to get rid of that overlap clearly, because that overlap is not good for bandwidth efficiency. So, okay, I'm not going to spend more time, but hopefully this gave you an example of a more sophisticated prefetcher than what we have discussed so far. And existing prefetchers are all more sophisticated. Let me put it that way. Okay, and there are even more sophisticated prefetchers that try to minimize the bandwidth waste. So clearly this prefetcher can cause bandwidth waste also, depending on the circumstances and depending on the requested issues. Okay, so this is a locality-based prefetcher. This is bandwidth intensive, as I mentioned, and I think I mentioned the why, because they look at a tracking window, and if requests keep coming into the tracking window, they prefetch further into the window, and they move the window. So even one request may lead to 3 or 4 prefetch requests. Even one demand request that fits in the window may generate 3 or 4 demand requests, or one demand request potentially, right? And as a result, they could be bandwidth intensive, and this could be fixed by stride detection and feedback mechanisms, which we will talk about. We talk about stride detection mechanisms already. And they also limited to prefetching close by addresses. What if you have large jumps in addresses access such that your tracking window doesn't cover them, right? So if you're going, for example, from A to A plus 1024, well, your tracking window may cover them if your tracking window is huge. But if your tracking window is huge, then you have a problem with bandwidth intensiveness even more. So you need to be careful in the design of these prefetchers. And somehow you may need to actually figure out how to do these large jumps in prefetching, because some of these large jumps can be regular. For example, you have an outer loop and an inner loop, and the outer loop accesses that you have, the loads that you have in the outer loop, maybe actually have a stride, but they may have a stride of, I don't know, 10,000, right? You always access every 10,000 element or 64K elements, right? Because you go through very large arrays, let's say. So it's important to actually try to prefetch those also. Software prefetching can actually do those better. If you think about it, outer loop prefetching can potentially be done by software prefetching more easily because the address streams are large. But you need to actually look at the trade-offs. So, however, these prefetchers, these locality-based prefetchers, work actually really well in real life. And I've implemented multiple of them in my thesis, for example, plus while I worked at Intel. And they actually work really well in real life. And this is an example from single core systems. And I copied this picture from Intel Prescott processors paper that describes an Intel Prescott processor, which is a version of the Pentium 4. And you can see that the relative performance on these workloads compared to no prefetching, prefetcher disabled, is significant. So you can see some workloads gain 16%, some workloads gain 97%. Some of these clearly have predictable access patterns, but the performance improvements are very significant, as you can see. With prefetching, it's you can see high performance improvements basically because you're covering a lot of the latency if you're doing things right. Okay. So this slide is not just about limitations, but also positives of locality-based prefetchers. Okay, so let's talk about prefetcher performance metrics a little bit. Even though we've introduced all of these in some way, I'm going to introduce them again. Accuracy is used prefetchers divided by sent prefetches by the prefetcher. coverage as prefetched misses in the program divided by all misses in the program. So clearly, you would like to maximize coverage to 100%. You would like to also maximize accuracy to 100%. Not always, because unless if this comes with a trade-off, right? Timeliness is how many prefetches are on time divided by used prefetches. As we've discussed, there are multiple measures of timeliness potentially. I'm not going to talk about them again. On top of this, there are two metrics that are not as much discussed, but they're important to discuss, which is bandwidth consumption and cache pollution. You can also add energy consumption over here. Bandwidth consumption is memory bandwidth consumed with the prefetcher divided by without the prefetcher. So this clearly you would like to minimize this as much as possible, but sometimes there's no pain, no gain. So you may need to consume more bandwidth to get benefit. But sometimes you can utilize idle bus bandwidth, so it may not be important to consume more bandwidth, right? Because the bandwidth is idle. So cache pollution is a bit harder to quantify, but these are extra demand misses due to prefetch placement in the cache. But it's clear this affects performance. So prefetcher aggressiveness affects all performance metrics. Aggressiveness depends on the prefetcher type. For most hardware prefetchers, you have two things that determine the aggressiveness. One is prefetch distance, how far ahead of the demand stream you are, and the other is prefetch degree, how many prefetches per demand access you're generating. And we've discussed both of these implicitly, at least, when we talked about the locality-based prefetcher. The tracking window, for example, determines how far ahead of the demand stream you can get. Prefetch degree determines is how many prefetches you're sending per demand access that you get into the tracking window. And this could be, both of these could be configurable depending on how much, how aggressive you want to make the prefetcher. So pictorially, you have an access stream. This is demands, and you get an access X, and the predicted stream is ahead of it can be ahead P max of access X. So this is the prefetch distance. How far ahead from the last access you get from the processor. So clearly, this is a very conservative prefetcher that's not staying far ahead. This is a middle of the road prefetcher that's staying a little bit more ahead. And this is a very aggressive prefetcher that's staying very far ahead. So clearly the downside of very aggressive means your stream may not be used later on, meaning it may not be accurate, but this may increase your coverage and also timeliness. So clearly there's a trade-off. Accuracy, coverage, and timeliness is again, another of those three metrics of which you can get maximum of 2. Well, if you're careful, you can try to get more than 2, but usually they go against each other. Well, some of them go against each other, not all of them go against each other. If you want to increase coverage, you usually reduce accuracy. And if you want to increase timeliness, you usually need to increase coverage, which means that it comes at the expense of accuracy, right? So that's the idea, basically. Okay, so let's look at prefetch degree. So prefetch degree is whenever you get a new demand access, how many prefetches do you issue? So in this case, prefetch degree is 3 because you're issuing 3 prefetches in the prefetch access stream whenever you get a demand access in the demand access stream. Okay, so hopefully that's clear. Clearly, you can make this not so very conservative, middle of the road, and very aggressive as well. You can issue 16 prefetches, right? Like we have discussed earlier, potentially, and that will be very aggressive. Okay, how do these metrics interact? I've given you some interactions, but let's talk about this. Very aggressive prefetcher has large prefetch distance and prefetch degree. Very conservative prefetcher has small prefetch degrees and small prefetch degree. So let's take a look at how these metrics interact in these. Clearly, if you have a very aggressive prefetcher, you're likely well ahead of the load access stream, unless the load access stream jumps to some other location, which may happen when you go into some other data structure, for example, or yeah, it can happen basically, or when your data structures may be extremely large that you're traversing over. But this hides memory access latency better, but it's also more speculative. Whereas very conservative prefetcher stays closer to the load access stream, it may not hide memory access latency completely, but it does reduce potential for cache pollution and bandwidth contention. So very aggressive prefetchers usually have higher coverage and better timeliness, but likely lower accuracy and higher bandwidth and pollution, cache pollution. And you would expect exactly the opposite for the very conservative prefetcher, right? These have likely higher accuracy, they consume lower bandwidth, and they're less polluting, but they likely have lower coverage. And as a result, as a result of the fact that they're closer to the load access stream, they're less timely. So these are 2 examples. Clearly, you can build prefetchers that trade off different metrics from each other into the algorithm. into the aggressiveness, etc. But this is a treatment of all prefetchers in a prefetch algorithm and type independent manner. So all prefetchers can be very aggressive. All prefetchers can be very conservative by how you decide, depending on how you decide prefetch distance and prefetch degree. Algorithm itself may make a prefetcher more aggressive and more conservative, and that's algorithm specific, of course. And I'm not going to talk about that as much. But any algorithm you can make more aggressive or more conservative by changing these two parameters, prefetch distance and prefetch degree, regardless of how you design the prefetcher, software, hardware, cooperative, execution-based, etc. All of them can be modulated based on prefetch distance and prefetch degree. Okay, so let's take a look at the effect of prefetcher accuracy on percentage improvement with prefetching, let's say, compared to a no prefetching baseline. So this shows some correlation clearly, right? Accuracy 1 means it's 100% accurate. Accuracy 0 means it's 0% accurate, and everything is in between clearly. But clearly you can see some correlation, but it's not a perfect correlation. So whenever your accuracy is terrible, you lose some performance in these workloads. And these workloads are some workloads that I'm going to show you later in the paper. Whenever your accuracy is reasonably high, you gain some performance. But extremely high accuracy doesn't mean the highest performance gain. And low accuracy, well, relatively low accuracy doesn't mean the lowest performance gain, right? You can see that the highest performance gain happens here. And you can see there's a huge performance gain because memory latencies are very high. So 70% accuracy. So operating over here seems reasonable, maybe. This is a very aggressive prefetcher, by the way. This is an extremely aggressive prefetcher. It may not be terribly aggressive, actually, compared to some of what's implemented, but you will see that you can do much better by modulating the aggressiveness of the prefetcher. So you don't want to lose 50% performance on some workloads. You don't want to lose 20% performance on some workloads. Sometimes, actually, because systems lose performance because they have irregular access patterns, prefetchers are turned off in some of those systems. Server systems, for example, turn off prefetchers because they think the accesses are irregular and these prefetchers don't do too well. Okay, so let me give you the results with real workloads that we have examined in 2007, this paper in 2007. You can see that no prefetching performs poorly. Very conservative prefetching performs better. Middle of the road prefetchings perform better. This is geometric mean average across all workloads. Very aggressive prefetching performs highest. But unfortunately, it loses performance in some workloads a lot. So you don't want that to be happen. And some workloads a little, but still. And some workloads, it keeps getting performance. So ideally, you would like to adapt to when this mechanism works well. Sometimes when you become very aggressive, you lose performance, right? When you're middle of the road, you don't lose performance. You actually gain performance. And this instructions per cycle. And it's not normalized, as you can see. It's a single thread. It's basically the baseline instructions per cycle without prefetching is this blue one. Okay. So the basic idea in throttling the prefetcher is you dynamically monitor prefetcher performance metrics. It's a very simple idea. You dynamically monitor but it works with any prefetcher that you can potentially design as long as you can modulate prefetch distance and prefetch degree. The idea is you have a hardware structure that dynamically monitors prefetch performance metrics. I'm not going to go into exact detail on how you do that, but you can find mechanisms of doing that and throttle the prefetcher aggressiveness up and down based on past performance. And we also change the location of prefetches inserted into the cache based on past performance. We discussed MRU, most recently used, least recently used, or middle positions. And you can actually insert, if your aggressiveness, I will show you actually in a little bit. So you check accuracy metrics, how accurate the prefetcher is, and you classify it into 3 groups in this particular case. And you check the timeliness of the prefetcher. And if the prefetcher is highly accurate but not timely, but it's polluting, you decrease the aggressiveness of the prefetcher. Why? Because the hope is that it's not late, but it's polluting. By decreasing the aggressiveness, you make it less polluting. Okay. Well, of course, you need to keep track of these metrics somehow. I refer you to the paper for that. There could be simple hardware mechanisms to keep track of that. But if you're high accuracy and late, we increase it so that we can actually make the prefetches more accurate. We increase the aggressiveness so that we can make the prefetches more accurate. Okay. And then you can actually look at these things. Let me look at this one. If you're low accuracy but not polluting and not late, we don't change it basically. If you're low accuracy otherwise, meaning polluting or late, then we decrease the aggressiveness even more because you're not accurate. In this case, we don't take into account coverage because we didn't find a good way of taking into account coverage, but a later work that builds on this work takes into account coverage as well. But you can look at those works. This is the first attempt at modulating the prefetcher in terms of multiple different metrics, in terms of both performance and also bandwidth consumption and pollution. And if you actually use this mechanism, there could be better ways of actually doing these heuristics. Potential machine learning mechanisms could work really well here, actually. But I'm not going to go into those. If you actually do this dynamic aggressiveness and insertion, you actually gain even better performance compared to no prefetching and the very aggressive prefetching, which was the best. So these are the two bars. We gain even more, as you can see. And we curb those cases that lose a lot of performance. For example, these were losing a lot of performance with actually any prefetching almost. But now we gain performance with prefetching for these workloads by throttling the prefetcher accordingly. And sometimes you're not the best. Sometimes the throttling mechanism is not making the best decisions, as you can see. You could gain even more over here by getting closer to very aggressive or by doing better than very aggressive, but we're not doing very well. But still, we're doing much better than no prefetching, right? So you can see that this sort of throttling mechanism is actually very effective. And the paper actually discusses its application to multiple different types of prefetchers. So let's talk about memory bandwidth usage. So I'm going to talk about bus. This is usually measured by memory bus access per 1,000 finished instructions. So this includes the effects of L2 demand misses as well as pollution-induced misses and prefetches clearly. This is a measure of bus bandwidth usage. And I like this measure because it's bus accesses per 1,000 instructions. It gives you how often you're generating a bus access relative to the number of instructions you're finishing. And you can see that this is the IP instruction per cycle average across many workloads and this bus bandwidth metric. You can see that no prefetching has low instructions per cycle. Very aggressive prefetching has the highest instructions per cycle. And feedback-directed prefetching actually has the highest compared to the best previous. And no prefetching has a bus accesses per kilo instruction that's like this, 8.5. Very aggressive prefetching increases it a lot, but feedback-directed prefetching actually reduces it significantly. So you basically get better performance than the best performance that you could achieve while consuming bandwidth like a middle-of-the-road aggressive prefetcher, right? That's the idea over here. So the performance that you get per bandwidth you consume is much higher than actually any of these prefetchers if you do the calculations, including no prefetching baseline. So if you actually divide these two metrics, performance per bandwidth, which is a good approximation of efficiency of the prefetcher or energy efficiency as well, because bandwidth is really energy, then you will see that this throttling-based mechanism provides the highest. And I believe this gets the second highest, the middle of the road over here. Okay, so if you're interested, you can read this paper. This actually may be one of the readings in your next homework going forward. There's a lot more in this paper that than what I have discussed. For example, where do you insert the prefetch into the cache? Does a prefetch buffer help or doesn't help? So it's good to look at it if you're interested in prefetching. It's a very comprehensive coverage of how to modulate prefetchers. And the good thing is it's applicable to any prefetcher, in my opinion, as long as you can somehow modulate prefetch distance and prefetch degree. Okay, now let's go into even harder stuff. Basically, harder stuff means more irregularity. How do you prefetch more irregular access patterns? So regular access patterns, stride, stream prefetchers do reasonably well. Locality-based prefetchers do reasonably well. Of course, you can make them even better. But more irregular access patterns are even more difficult. And these come from clearly data structure accesses, right? Indirect array accesses, linked data structures that we discussed, multiple regular strides. These are actually relatively regular. I've already mentioned that, but these could be handled by adapting the earlier prefetchers that we discussed so that they can keep track of multiple regular strides, patterns and strides, let's say, or adapting what we're going to discuss next. So these actually fall somewhere in between. And then completely random patterns, can you prefetch them? And we kind of discussed that, oh, if you're execution-based, maybe you can prefetch completely random patterns, right? And then can we come up with a generalized prefetcher for all patterns? Or do we need to have hybrid prefetchers, right? So I'm going to discuss three different types of prefetchers: correlation-based, content-directed, and pre-computation or execution-based prefetchers. So let's jump into it. And all of them are actually quite cool ideas. This was correlation-based prefetching ideas were introduced in late 1990s, 1996, 1997, and they were done concurrently by Dirk Grunwald's groups, Doug Joseph and Dirk Grunwald. That's the paper I'm going to based on, but also by Mark Charney in his PhD thesis at Cornell, which was, I think, not published in a top conference, but they were concurrent work. Essentially, correlation-based prefetching means that based on what I've seen in the past in terms of the correlation between addresses, I'm going to predict probabilistically another address. It's as simple as that. Let me give you an example of why this may make sense. Right? Consider the following history of cache block addresses, and let's assume that all of them are misses for whatever reason. You keep repeating this, okay? When I look at this, after I get A and B, I get C after that, right? How many times does that happen? Okay, A and B, I see C. Or A and B, I see C. Okay, there's some correlation here, right? If I see A and B consecutively, maybe I should prefetch C. Does that make sense? Yeah. Well, it makes sense. So I can keep learning these correlations, right? I can either keep learning these correlations using tables or maybe using machine learning, potentially, right? But this work actually introduced correlation-based prefetching using tables that are not based on machine learning, based on memorizing what had happened. I mean, similarly, you can say after D, I usually see C. And well, it's not true here, but it's true here. So basically, for a given access pattern over time, you can form a Markov table, let's say, Markov model. So after referencing a particular address, some addresses are more likely to be referenced next. And you can figure this out by keeping track of what you've seen after you referenced one address, and by connecting them using what's called the Markov decision graph or Markov graph, or also Markov model. And what is a Markov model? Basically, you have these states which describe the address that you've seen, and state transitions which describe what address you're going to see next based on what you've seen so far, and the probability of that transition. That's the idea. It's very simple. And you can actually imagine potential reinforcement learning mechanisms that go through this Markov model and Markov decision process. Of course, how do you figure out new addresses remains a question. This will be an issue in this table also, actually. But basically, the Markov model for this access pattern is after A, with 60% probability, I see B. After A, with 20% probability, I see A again. After A, with the remaining probability, I see C. Okay. After B, with 100% probability, I see C. Okay. And then now you can chain the probabilities. After A and B, I see C most of the time. Basically, you can do probabilistic calculations on top of this, right? Okay, that sounds good, right? So now you can record, whenever you see an address, you can record the most likely address after that, or maybe all of the addresses that come after that and the likelihood of those addresses. Now you can record all of these in a table, basically. Of course, this table may become large. And the next time you see address A, you say, okay, with 60% probability, I'm going to prefetch address B. And with 20% probability, I'm going to prefetch address A again, if that makes sense, of course. And with 20% probability, I'm going to prefetch address C. Does that? Oh, hopefully this is clear, right? Basically, you form a correlation table, and you can actually make this correlation table even more complex by correlating between A and B together. Basically, by essentially fusing the states over here, if it's possible to do, or if it's interesting to do. That way, you gain more confidence potentially before you make a prediction. Right? Okay, so basically, I've given you the idea already. Record the next likely addresses after seeing address A. And next time A is accessed, prefetch those next likely addresses. And this is a correlation-based prefetcher because A is said to be correlated with B, C, D. And here's how you do it. Basically, it's a cache block-based prefetcher. You record on a cache block you've seen, what are the next addresses that you've seen? These are prefetch candidates. And you may have a confidence, which is the probability of access based on past, potentially. And you correlate. And this was introduced in this paper, seminal paper in ISCA 1997, as you can see over here. And how you can increase coverage by prefetching up to n next addresses. You can see you can prefetch this one, this one, this one, all of the prefetch candidates given a cache block address. You may have an accuracy problem here if you prefetch everything, of course. And you can improve prefetch accuracy by using multiple addresses as key for next address. So for example, you don't keep track of correlation between one single address and the next addresses, but you keep track of correlation between two addresses coupled or fused with a next address. So in this case, A and B said to be correlated with C. Of course, your table structure needs to be different right now. You may need to hash into your table using two addresses. Okay. So hopefully this is interesting. And you can also prefetch ahead by actually, whenever you get a prefetch, where you reindex the table, and then you get new prefetch candidates based on the prefetch. So you got to be very careful, of course, if you do that, because now you can be very, very speculative. Because depending on how many addresses you have, clearly this is an exponential search. Because if you get prefetch addresses, 3 prefetch addresses here, and then 3 prefetch addresses for each prefetch address that you index, next time you generate 9 prefetch addresses, right? 3 times 3. Okay. So these are also called Markov prefetchers, as you can see, and this is a cool idea. And later work that came after this tried to reduce the size of the table over here, and there's some degree of success, some degree of not success. As a result, this is not an easy thing to build, actually. So let's talk about advantages and disadvantages before we talk about ease of building. So this can cover arbitrary access patterns. Now you have linked data structures that you're traversing, A, B, C, D, E, F, G, that have nothing to do with each other. You traverse them once, and then you go back to the loop and traverse them again. Well, now you recorded what you traversed, and hopefully you'll prefetch nicely. And it can also record streaming patterns, right? If you're prefetching address, let's assume that you have a big loop. You prefetch address A with stride 4, I don't know, 10,000 times, meaning A plus 4, A plus 8, ... until you go to address A plus 40,000. And then you record all of these in a table. It's a bit crazy, yes. You record every single one in the table, not so good. But if you have a large enough table size, you could do it. And then when you actually go through the streaming pattern again, you have to do this again, unfortunately, because that's the limitation of the Markov-based prefetching. You memorize what happens. And if it happens again, you can prefetch it. So you see A next time again. Now you can prefetch address A plus 4. If you see A plus 4, you prefetch address A plus 8, ... right? And you can actually link these prefetches, as I mentioned. You prefetch, whenever you see address A, you prefetch address A plus 4, but then you reindex into the table with address A plus 4, you prefetch address A plus 8, you reindex into the table, you prefetch address A plus 12, ... Clearly, it's a lot of work, but you could do it potentially. So even streaming patterns can be covered, but not so efficiently, right? So this is relatively arbitrary, but not necessarily efficient in any pattern. So there are disadvantages. One of the disadvantages will be that basically correlation table needs to be large for high coverage, and recording every misaddress and its subsequent misaddress is usually infeasible, especially if you're operating with huge data structures. Let's assume that you're traversing a 1 million entry linked list. Do you really have 1 million entries in your correlation table? Okay, 4 million, 16 million, 1 billion. Well, too bad, right? So your correlation table can quickly become unwieldy, and that's one of the reasons why this mechanism is not employed, as far as I know, in processors. And it also can have low timeliness. Look at it is limited since a prefetch for the next access is initiated right after the previous. But you can fix these issues, as we discussed, by indexing into the table using the prefetch address and then generating the next prefetch, etc. Prefetching for more addresses, maybe recording more addresses downstream into the correlation table. All of them come up with latency penalties and increasing the size. They may come up with penalties of increasing the size of the correlation table. Okay, so it's not easy to build basically. And it can consume a lot of memory bandwidth, especially when Markov model probabilities or correlations are low basically. And especially if you want to have high timeliness. So these prefetchers are, while they're a really interesting idea, they're usually not very practical. But it's important to cover these prefetching ideas because it's a good idea. And one last disadvantage of this is clear this cannot reduce, even though it's a prefetcher, it cannot reduce compulsory misses. You have to see the access pattern once to be able to prefetch what comes after. So you have to see A, B at least once so that you can say, next time I see A, I'm going to prefetch B. Because before seeing that, you don't have anything in your correlation table. Right. So you cannot, as a result, reduce compulsory misses. Contrast this with streaming predictors that we discussed earlier that latch on a stride or stream. They do not need to see address A+4, let's say address A+8, so that they can prefetch address A+8 if they've seen address A and address A+4. But that's not the case for Markov prefetcher. Even if you're using Markov prefetcher as a stream prefetcher, you're not going to be efficient, but you're also not going to be able to capture the stream for the first time. The next time you see the stream, yes, you're going to capture it and prefetch it, but for the first time you have to memorize what went on. So they're based on memorization, basically. They're not based on detection of a formula, let's say. That's the reason why they cannot reduce compulsory misses. Anything that's based on memorization and done a model cannot reduce compulsory misses, right? Caching is based on memorization, it's reactive. This is also reactive. This is really, in a sense, caching the correlations between different addresses, right? It's no different from caching from that perspective. And it's based on memorization. Whereas a stream prefetcher, for example, or a stride prefetcher, or a sophisticated version of that is based on some formula that it figures out. The formula may be relatively complex. It may not be written down like in a locality-based prefetcher, but it's still based on some formula. And based on that formula, you can generate new addresses, right? So it's based on, or that formula can also be called a model, right? You're really modeling the access pattern in some way based on what you've seen. Whereas here, the model is not formulaic, the model is really memorization. So it's good to keep that in mind. Okay, let me talk about another idea, which is also fascinating, content-direct prefetching. This is a specialized prefetcher for pointer values. And the idea is to identify pointers among all values in a fetch cache block and issue prefetch requests for them. And it has a cool heuristics for identifying pointers. And it was introduced in this paper in ASPLOS 2002. And the huge advantage of this is there's no need to memorize or record past addresses. So this could be stateless, as you can see from the perspective of storing addresses. That's why I like this idea. It's a creative idea where you don't need state. It can eliminate compulsory misses, never seen pointers, basically, because you just scan the cache block to find likely pointers, and it prefetch them. Of course, you need to be able to bring a cache block first and scan that cache block, and then you can prefetch pointers, and then those bring new cache blocks, and then you can scan them again. So you could keep doing this forever. So you can increase your prefetch distance and prefetch degree that way. So you can eliminate your compulsory misses by traversing through data structures this way. Of course, the downside is this indiscriminately prefetches all pointers in a cache block. So maybe you want to be a little bit more intelligent, and maybe software can guide you in that. And I'm going to briefly describe a work that does it, but I'm not going to tell you exactly how it does it. So of course, there's a question over here. How do you identify pointer addresses? And this paper uses a cute mechanism. It basically compares address size values from the cache block with the cache block's address. If the most significant few bits match, then you declare that it's a pointer. Of course, software can tell you exactly what's a pointer, but that requires an interface and some bits in your cache block. But this is a heuristic that's used to say, okay, if my top most significant bits match, let's say my top 12 bits match of the size of the cache block address, and with the address size values I have in the cache block, then I think that this address size value within the cache block is a pointer. Okay, I'm going to give you an example of this. So this is called a virtual address predictor. Of course, this works nicely with the virtual address space because pointers are in the virtual address space clearly, right? Keep that in mind. They're not in the physical address space because in a virtual memory-based system, you program with virtual addresses. And I'm going to give you an example of this. So let's assume that this is the cache block address that's requested by the processor. You access L2, you miss. You access DRAM, you miss. And eventually you get the cache block at the cache block address. Now what we do is basically, by the way, are people hearing this annoying sound? I just want to make sure what you're hearing or what you're not hearing. Can anybody tell me? There's a drilling sound right above my head.
Yes, we can hear it, but
okay,
it's not a problem.
Okay, it's not a problem. So, okay, it's annoying to me, but as long as it's annoying to you, I will continue because I think it's good to finish some part of prefetching and we will handle the next lecture accordingly. Okay, good. So basically, this is the cache block, the address of the cache block, and this is the cache block itself. So this is 64 bytes. Assume that address is, I don't know, 8 bytes over here, right? Yeah, it's 8 bytes over here. Basically, you chop the cache block into 8 byte entries and say these are potential addresses, and then you compare each of them to the address over here. But you compare the top 12 bits. That's the idea over here. So let's take a look. So you basically chop up the cache blocks values, the data values essentially, into 8 pieces of 8 bytes, because pointers are 8 bytes. Let's assume that. You would know that when you're designing the system clearly. And you basically compare each pointer sized value to the address of the cache block. And you compare, of course, the top 12 bits in this case. And the paper discusses how many bits you should compare to ensure that you get the false positive. You don't get a lot of false positives or false negatives in the end. And if you do this comparison, in this case, you will see that only one of them match, right? Well, I didn't show these over here because they're basically far away from this, let's say. And this may be a pointer, but that doesn't match. Unfortunately, you will miss that. But none of the other ones are pointers, let's say. Maybe all of the values are -1, let's say. But this one matches. Now this matches. This means that for the content-directed prefetcher, there's a pointer, and the content-directed prefetcher issues a prefetch for this address, which is clearly different from this address, right? And then you prefetch, and then that brings another cache block, and then you examine that cache block. And then you may decide to prefetch some items in that cache block. So this way, you're basically pointer chasing in your prefetcher without requiring any state. Why? Because you're just examining the cache blocks you prefetched. Or fetched. Okay, that's a cute idea. And this paper that I mentioned from ASPOS 2002 shows that it improves performance. It actually looks at very difficult to prefetch workloads. It was done collaboratively with Intel, so there's a lot of Intel workloads that are interesting in there. I would recommend looking into that. But they also say that sometimes this works badly because you actually lose performance because you're prefetching too much, because you see a lot of pointers over here. So we improved that later on by making content-directed prefetching more hardware-software cooperative. And the fundamental issue is hardware doesn't have enough information on pointers and data structures. Now, we've said this multiple times in the course of this lecture. Let's communicate more information to the hardware such that it has more information about pointers, where software knows what is a pointer and what's not. And it may know what's a pointer that's likely to be accessed and what's a pointer that's not likely to be accessed. And it can also get profile information. It can also profile the code, and it can decide these pointers may be likely accessed and these pointers may not be likely accessed. So this is a hardware-software cooperative mechanism. And the key idea is compiler, or even the programmer, but we try to shy away from making programmers work harder. Compiler profiles and analyzes the code, and provides hints as to which pointer addresses are likely useful to prefetch. And these hints get communicated to the prefetcher. And the hardware uses hints to prefetch only likely useful pointers in a content-directed prefetching engine. And this significantly increases the performance and efficiency of content-directed prefetching. I'm not going to go into details, but let me give you an example from a minimum spanning tree application. So if you look at, but this hash lookup exists in many applications. Basically, you're looking at a hash table bucket. And you basically, in a hash table bucket, you're basically traversing the hash table, well, you're not traversing the hash table, sorry. You're traversing the linked list that's in that particular hash table entry, and this is what's showing the traversal. Assume that you have a large number of entries in the bucket. What you need to go through is you compare the key that you're looking up to the key that's stored in each node, and you do that until you find a node that houses the same key, or until you basically exhaust the linked list. Right? That's the code for this, clearly. And this is what happens. This is what it looks like in a cache block. So in a cache block, you have a pointer to the key, and each key has a pointer to D1, D2, ... And this is how things get laid out in a cache block, right? Okay. So in a cache block, you actually, assuming that these are laid out consecutively in memory, in a cache block, you would have all of these pointers, right? Let's take a look at that. So a cache block looks like this, actually. You have the key, you have the D1 pointer, D2 pointer. These are the two data pointers that you have. And then you also have the next pointer. So clearly, key hopefully is not a virtual address, but these three are pointers. So in a cache block, you have 6 pointers over here. So if you use the vanilla or proposed content-directed prefetching algorithm, you may get a match on all of these 6 pointers, right? Whenever you get the cache block, you have 6 pointers, and you prefetch 6 pointers. Now that may not sound very good, right? Why? Especially if you look at this code, you may say the likelihood that I'm going to need the D1 and D2 is not very high, right? Especially if you know more about your linked list. If your linked list is, I don't know, 1,000 elements. The probability that, assume that you have unique key stored, you're going to find the key in at most 1 element, meaning you'd better examine the keys or next nodes clearly. But you really don't need the data, D1 and D2, for more than 1 element. And likely you don't need it for any element, potentially, right? If your key doesn't exist in the hash table. So that's the idea, basically. Based on the knowledge of the data structure and potentially the behavior of potential input sets, you decide which pointers to prefetch. You convey it to the hardware, and you convey, in this case, that next is much more likely to be needed than D1 and D2. And the hardware, instead of prefetching 6 pointers, it prefetches just the next ones, and these 2. That's the idea, basically. Okay, so I'm not going to go through this. It basically says you're going to prefetch just the next ones, maybe both of them, maybe one of them, I don't know, depending on how things match. Okay, so if you're interested in it, you can take a look at this work that talks about it. A bunch of other ideas also in this work. Basically, this work looks at how do you actually do better in the prefetching of linked data structures, how it can be much more bandwidth efficient, and how you can combine these different prefetchers with stream prefetchers and potentially other prefetchers as well. Okay, so let me cover some more and find a good place to stop, and then we're going to continue tomorrow. But basically, hopefully it's clear to you that there are many different access patterns in programs: streaming, striding, linked data structures, localized random, completely random, etc. And it's very difficult to cover all patterns with a single prefetcher. So the idea is really to use, idea in hybrid hardware prefetchers is to use multiple prefetchers to hopefully cover all or more than one pattern at least. And this gives you better prefetch coverage so that you can cover more patterns over here. But of course, with anything hybrid or heterogeneous, you get more complexity, more bandwidth intensity, and prefetchers may also start getting in each other's way. They may cause contention, pollution, and you may need to manage accesses from each prefetcher. And this work actually tackled some of those problems because it really talks about hybrid prefetching for both linked list and streaming accesses. Linked lists can be random depending on how the memories are allocated and how you're traversing. Streaming is clearly not random, right? But if you combine 2 of these prefetchers in a hybrid prefetching system, then you need to modulate different prefetchers. And clearly this work is one of the first that looks at that problem in the multiple prefetching systems. And in the end, prefetcher design is getting more complicated today because clearly data movement is a bottleneck, and you would like to minimize the latency effects on the processor, assuming you keep the processor-centric paradigm. And we are keeping the processor-centric paradigm for some time at least. Looking at how to design hybrid prefetchers is actually going to be even more important going into the future. Okay, I think this is a really good place to stop. We're going to pick up on this tomorrow and probably have a short lecture related to this, talking about only execution-based prefetchers. And then hopefully we're going to release also the assignment tomorrow, the programming assignment, which is on prefetchers. But hopefully we're going to have fun with some easy to implement prefetchers, not necessarily hard to implement ones. But you're welcome to also get bonus points by implementing some of the state-of-the-art prefetchers or hard to implement prefetchers. Okay, any questions at this point? Okay, feel free to ask questions on Piazza. And I think one of you, Johan, requested papers. Please remind me of that on Piazza. I think it's good to post these things on Piazza so that everybody can see them. But otherwise, I'm going to end here. And this is a good time to end here because this drilling is really drilling my head at this point. Maybe it's not drilling your head, which is good, which really is good news for the microphone manufacturer that I'm using, but it's certainly not protecting. The headphones are certainly not protecting me from getting my head getting drilled. Okay, so I'm going to stop here. Let's continue this tomorrow. Okay, take care and see you tomorrow.